Hello there, and welcome to Nightfall Science. Tonight, we drift through the quiet evidence that life may exist beyond Earth. Let your shoulders soften and your eyes grow heavy as the stars keep their ancient watch. Let's begin. The first important truth is also the quietest one. Science has not yet discovered confirmed proof of life beyond Earth. No distant transmission has been verified as an alien message. No organism has been collected from another world. No atmospheric signal has yet passed every test required to call it biological. But this does not mean the universe appears empty. It means the search is still unfolding. Scientists distinguish carefully between proof, evidence, and possibility. A single unusual molecule may be interesting, but natural chemistry might also create it. A planet may orbit at a comfortable distance from its star, yet still lack air, oceans, or a stable climate. Even a promising radio signal must be observed again and traced beyond every possible source of human interference. The standard is deliberately high. A discovery this important must survive many different tests. Independent observatories would need to confirm it. Alternative explanations would need to fade away. Several lines of evidence would need to point gently toward the same conclusion. NASA describes this process as a ladder of life detection. Each step raises confidence. Simple organic chemistry stands near the bottom. More distinctive patterns appear higher up. A convincing discovery would rest near the top, supported by chemistry, environment, repetition, and context. For now, humanity has not reached that final step. Yet the lower steps are no longer empty. Organic molecules exist throughout space. Water appears in planetary systems, moons, comets, and clouds between stars. Thousands of planets circle distant suns. Some are rocky. Some occupy regions where temperatures may permit liquid water. Telescopes can now begin reading the chemistry of their atmospheres from across immense distances. None of this is proof by itself. Together, however, it changes the question. The universe no longer seems like a dark ocean containing one known island. It resembles an ocean filled with shores that are only beginning to emerge through the mist. The proof has not arrived, but the places where proof might be found are multiplying. The story begins with a census of distant worlds. Only a few decades ago, no planet beyond the solar system had been confirmed around a star like the Sun. Astronomers suspected such planets existed, but suspicion remained separated from observation. That changed in 1995. The planet known as 41 Pegasi b was found circling a Sun-like star. It was unlike anything in the solar system. It carried roughly half the mass of Jupiter, yet completed an orbit in only a few days. This enormous world drifted extremely close to its star. Its discovery revealed something unexpected. Other planetary systems did not have to resemble the familiar arrangement around the Sun. Worlds could appear in strange sizes, unusual locations, and tightly packed orbits. Nature had built planets with far more variety than the first theories imagined. More discoveries followed. Some planets were detected because their gravity gently pulled on their stars. As a planet moved through its orbit, the star made a tiny answering motion. Its light shifted slightly toward blue and then toward red. This repeated wobble revealed the presence of an unseen companion. Other planets were found when they crossed in front of their stars. During each crossing, called a transit, the star became a little dimmer. The change might be less than 1%. Yet sensitive telescopes could measure that delicate rhythm. One dip could be noise. Repeated dips at regular intervals could mark a planet completing orbit after orbit. The method transformed tiny changes in starlight into maps of distant solar systems. A planet remained invisible as a separate point of light, but its shadow told a story. By 2026, the confirmed total had risen beyond 6,200 exoplanets. Thousands of additional candidates still waited for careful verification. Each confirmed world represented a place that had once existed only as an idea. The night sky had remained visually unchanged, but hidden within it, thousands of new worlds had quietly appeared. The planets already discovered represent only a small sampling. Most exoplanets cannot be detected with present instruments. Many do not cross their stars from Earth's point of view. Others are too small, too distant, or too widely separated from their suns. Their signals become lost within the motion and brightness of the stars around them. This creates a simple but powerful realization. Every confirmed planet suggests a much larger population that remains unseen. NASA's Kepler Space Telescope helped reveal this hidden abundance. Kepler watched more than 100,000 stars, searching for repeated dimming caused by planetary transits. It did not examine the entire galaxy. It studied a narrow region of the sky, like looking through a small window into an enormous landscape. Even through that window, planets appeared everywhere. Kepler confirmed more than 2,600 worlds. Many systems contained several planets. Some were compact arrangements where multiple worlds completed their years in only days or weeks. Statistical studies then used Kepler's discoveries to estimate what lay beyond its limited view. The results suggested that planets are not rare decorations around unusual stars. They are ordinary products of star formation. NASA estimates that the Milky Way contains at least 100 billion planets. Other interpretations of Kepler's findings suggest the true number could reach into the trillions when multi-planet systems and smaller worlds are included. The scale is difficult to hold in a single thought. If each planet were represented by one grain of sand, even a large beach would struggle to contain the galaxy's worlds. Many would be gas giants, many would be frozen, others would orbit so near their stars that their surfaces might glow. But among such vast numbers, even rare conditions can appear many times. If only one planet in a million offered a stable environment for simple life, a galaxy containing hundreds of billions of planets could still hold hundreds of thousands of possible habitats. That calculation does not prove that life begins there. It simply shows how many times the universe may roll the same quiet dice. Small rocky planets also appear to be common. This finding matters because life on Earth develops upon a rocky world. Earth has a solid surface, active geology, liquid water, and an atmosphere that exchanges material with oceans and stone. These systems help maintain a long-lived environment where chemistry can grow increasingly complex. Early planet searches often found large worlds first. This did not necessarily mean giant planets were more abundant. Large planets simply produced stronger signals. Their gravity moved their stars more noticeably. Their broad shapes blocked more light during a transit. Finding an enormous planet resembles hearing a large bell across a quiet valley. Finding an Earth-sized planet is more like noticing the movement of a distant blade of grass. As instruments improved, smaller worlds began to emerge. Kepler revealed planets slightly larger than Earth, planets roughly Earth-sized, and worlds between Earth and Neptune in size. That middle category is especially interesting because it does not exist in the solar system, even though it appears common elsewhere. Analysis of Kepler data suggests that between 20 and 50% of visible stars may host small, possibly rocky planets within their habitable zones. Another study focusing on stars similar in temperature to the Sun concluded that roughly half could possess a rocky world capable of supporting surface liquid water under suitable atmospheric conditions. These are estimates rather than complete counts. Some stars may have planets that remain undetectable. Some objects first thought to be rocky may carry deep atmospheres. Others may have lost their air long ago. Still, the broad picture is gentle and clear. Earth-sized worlds are not unique constructions appearing only once in cosmic history. The universe seems able to build small planets repeatedly, from the same elements that formed Earth. Iron, silicon, oxygen, carbon, and water are not confined to one system. They drift throughout the galaxy, gathering around young stars and slowly becoming worlds. A planet's location can offer the first clue about its possible climate. Astronomers often speak of the habitable zone. This is the region around a star where a rocky planet might maintain liquid water on its surface. The zone lies farther out around hot, bright stars and much closer around cool, faint stars. It is sometimes called the Goldilocks zone. The name creates a simple image. One orbit may be too warm, another may be too cold. Between them lies a region where temperatures could be gentle enough for water to remain liquid. But the habitable zone is only a starting point. Venus sits near the inner region of the Sun's habitable zone, yet its dense carbon dioxide atmosphere traps enormous amounts of heat. Mars occupies the outer portion, but its thin atmosphere provides little warmth and pressure. Earth remains comfortable, not merely because of distance, but because many systems work together. Atmosphere matters, planetary mass matters, clouds, oceans, magnetic fields, geology, and the behavior of the host star all shape the climate. A world inside the habitable zone may be dry and airless. A world outside it might hide a warm ocean beneath ice. For that reason, astronomers do not treat the habitable zone as evidence of life. They treat it as a way to select promising places for deeper study. It is similar to finding a house with a light in the window. The light does not reveal who lives inside. It does not even prove the house is occupied, but it provides a reason to look more closely. Thousands of exoplanets have now been placed upon maps of temperature, size, and orbit. A smaller group falls within potentially comfortable regions. That group becomes a collection of quiet destinations for future telescopes. Habitability is not proof of biology. It is the stage upon which biology might someday be discovered. Some of the most intriguing stages lie surprisingly nearby. The TRAPPIST-1 system rests about 40 light-years from Earth. Its central star is an ultra-cool red dwarf, much smaller and dimmer than the Sun. Around it circle 7 rocky planets, all similar in size to Earth. The entire system is remarkably compact. All 7 worlds orbit closer to their star than Mercury orbits the Sun. Because TRAPPIST-1 is so faint, however, several receive amounts of energy that could allow moderate conditions under the right atmospheres. 3 planets, known as TRAPPIST-1e, TRAPPIST-1f, and TRAPPIST-1g, move within the traditional habitable zone. Their skies would look very different from Earth's. The neighboring planets might appear as visible disks rather than tiny points. Some could seem larger than the Moon appears from Earth. Their years last only days, because their paths around the small star are so short. The system offers several natural experiments at once. Each planet formed from related material. Each experiences a different amount of starlight. By comparing them, astronomers can study why some rocky worlds keep atmospheres while others lose them. Webb has begun examining these planets. So far, no definitive atmosphere has been identified around the worlds already studied, and several inner planets appear unlikely to possess thick air. The outer planets remain subjects of patient observation. Much closer lies Proxima Centauri b. It orbits the nearest star beyond the Sun, only about 4 light-years away. Its minimum mass is close to Earth's, and it circles within the star's habitable zone every 11.2 days. Proxima Centauri is an active red dwarf. Stellar eruptions may make conditions difficult, and the planet's atmosphere remains unknown. Still, its existence carries a quiet significance. The nearest neighboring star possesses a potentially rocky planet in a region where liquid water could be possible. No long journey through the galaxy was required to find such a world. One waited beside the very first star beyond the Sun. Mars preserves the memory of a world that was once much wetter. Today, its surface appears cold and quiet. Rust-colored plains stretch beneath a thin atmosphere. Water cannot remain liquid for long under most present conditions. It either freezes, evaporates, or disappears into the ground. But the ancient landscape tells another story. Orbital cameras reveal valleys shaped by flowing water. Broad channels cross the surface like the remains of vanished rivers. Some craters contain layered sediments that settled slowly beneath lakes. Ancient deltas still preserve branching patterns, where streams once entered deeper bodies of water. NASA's Curiosity rover explores one of these former environments inside Gale Crater. More than 3 billion years ago, water repeatedly filled parts of this basin. Sediment accumulated across the lake floor, preserving a record of changing conditions over immense spans of time. Curiosity has studied mudstones formed in that ancient lake. Their minerals show that the water was not always extremely acidic or chemically harsh. At certain times, the environment contained liquid water, essential elements, and possible sources of chemical energy. These are the basic requirements for microbial life on Earth. Nothing found in Gale Crater proves that organisms lived there. Rivers and lakes can exist without biology. Clay can form through ordinary reactions between water and rock. Yet ancient Mars appears to have possessed habitable environments. This distinction is important. A habitable world is not necessarily an inhabited world. It is simply a place where known life might have survived. Mars once offered locations where small organisms could potentially have lived beneath shallow water, within wet sediment, or inside protected spaces underground. The dry landscape seen today may therefore be the closing chapter of a much longer story. Mars was not always the silent desert familiar from modern photographs. It once held lakes beneath a different sky, while water moved gently across its surface and settled into the stone. Ancient Martian rocks also preserve organic molecules. Organic molecules contain carbon arranged in structures that can become chemically complex. Every known living organism uses them. Proteins, cell membranes, genetic material, and countless biological processes depend upon carbon chemistry. But organic does not automatically mean biological. Such molecules can form without life. They appear in meteorites, comets, interstellar clouds, and laboratory reactions. Finding them on Mars is therefore not the same as finding a fossil or a cell. Their presence remains significant because life requires suitable raw materials. Curiosity drilled into ancient sedimentary rocks and heated the powdered samples inside its sample analysis at Mars instrument. The released gases revealed several carbon-bearing compounds, including sulfur-containing organics preserved within mudstone billions of years old. Sulfur may have helped protect some of these molecules from destruction. The Martian surface receives strong radiation. Over long periods, this radiation breaks apart complex chemistry. Burial within rock can offer protection, while sulfur can help bind organic material into more durable forms. Later analysis revealed an even wider collection of Martian organic molecules. Some were larger and more chemically diverse than those identified earlier. Their origins remain uncertain. Geological reactions may have formed them. Material arriving in meteorites may have contributed. Ancient biology is another possibility, but the available evidence cannot separate these explanations. That uncertainty is not a weakness. It is part of the careful path toward discovery. Scientists search for patterns that non-living chemistry struggles to reproduce. They examine molecular structures, isotope ratios, geological context, and the way different compounds appear together. One molecule rarely provides an answer. A whole chemical system may eventually tell a clearer story. For now, Mars has offered ingredients rather than proof. Still, those ingredients rested within the mud of an ancient lake, on a world once touched by rivers. Carbon chemistry and liquid water occupied the same environment long ago. The stones have not revealed whether anything lived there. They have shown that some of life's familiar materials were present. Methane adds another quiet mystery to the Martian atmosphere. On Earth, much of the methane in the atmosphere comes from living organisms. Microbes produce it in wetlands, sediments, animal digestive systems, and environments with little oxygen. This makes methane an interesting molecule in the search for life. But methane also has non-biological sources. Water can react with certain rocks and minerals to release it. Heat beneath a planet's surface may drive additional chemical processes. Comets and meteorites can deliver carbon-bearing material as well. Curiosity has measured small amounts of methane near the surface of Mars. The concentration appears to change, sometimes rising above its usual background level before fading again. These changes are difficult to interpret. The methane could be stored underground and released through cracks. Seasonal temperature shifts might change how gases move through soil and stone. Geological chemistry may still be active below the surface. A biological source remains possible, but no observation requires one. The mystery becomes deeper because spacecraft studying Mars from orbit have struggled to detect the same methane. Instruments above the planet examine broad regions of atmosphere, while Curiosity samples the air close to the ground inside one crater. The two kinds of measurements may be observing different environments. Methane released near the surface might become destroyed or diluted before reaching higher altitudes. Local geological activity could produce brief pockets too small for orbiting instruments to notice. Unknown Martian chemistry may remove methane faster than current models predict. Each explanation remains under study. Methane therefore rests between several possibilities. It is not evidence strong enough to announce life. It is a clue that the chemistry of Mars is still not fully understood. The molecule may eventually lead toward geology, atmospheric physics, or biology. Whatever its source, it reminds science that Mars is not simply a finished world. Subtle processes continue beneath its dusty surface and within its thin air. Even a planet that seems motionless can still breathe in faint, uncertain traces. Beyond Mars, some of the most promising habitats hide beneath ice. Europa, one of Jupiter's large moons, has a surface covered by frozen water. Its pale crust is crossed by dark lines, ridges, fractured plains, and regions where enormous blocks of ice appear to have shifted and rotated. The landscape resembles broken sea ice, seen in Earth's polar regions. Europa's surface remains frozen because sunlight is weak at Jupiter's distance. Yet the moon does not depend entirely upon sunlight for warmth. Jupiter's gravity repeatedly stretches Europa as the moon moves through its orbit. The stretching is slight, but it occurs again and again. Friction generated within the interior produces heat. This process is called tidal heating. Evidence from spacecraft observations strongly suggests that beneath Europa's icy shell lies a global saltwater ocean. Although Europa is much smaller than Earth, that hidden ocean may contain more water than all of Earth's oceans combined. The water probably rests above a rocky interior. This creates an intriguing environment. Water may interact with minerals on the seafloor. Such reactions can release chemical energy. On Earth, similar interactions support ecosystems far below sunlight. Europa's surface also appears connected to the ocean below. Dark material across the ice may include salts transported upward. Webb observations identified carbon dioxide concentrated in a region of disrupted terrain. Researchers concluded that this carbon likely originated within Europa's internal ocean rather than arriving mainly from outside the Moon. Carbon, water, rock, and energy may therefore meet within the same hidden environment. None of this demonstrates that organisms exist there. Europa could possess a chemically rich ocean that remains completely sterile. Its water may contain conditions that limit biological processes. The ice above it may restrict the movement of useful materials. Yet Europa expands the idea of a habitable world. A planet or moon does not need warm sunlight shining upon an open sea. A dark ocean beneath many kilometers of ice can remain liquid for billions of years, warmed by the gentle pull of gravity. Beneath Europa's frozen plains, an entire ocean moves without ever seeing the sky. Enceladus offers an even more direct view of a hidden ocean. This small moon circles Saturn. Its bright surface reflects much of the sunlight that reaches it, making Enceladus one of the most reflective objects in the solar system. Near its south pole, long fractures cut across the ice. From these cracks, enormous jets release water vapor and frozen particles into space. The material rises above the moon like a delicate fountain, forming a broad plume. Some particles fall back to the surface. Others escape and help supply one of Saturn's rings. The Cassini spacecraft repeatedly flew through this plume. In doing so, it sampled material from an ocean without drilling through the ice. The moon delivered pieces of its interior directly into space. Cassini detected water, salts, silica particles, organic compounds, and molecular hydrogen. The silica grains suggest that warm water interacts with rock deep below the surface. Molecular hydrogen may also form through reactions between water and the rocky seafloor. These reactions are important because they can provide chemical energy. On Earth, microbes near hydrothermal vents use chemical gradients rather than sunlight. They live within dark environments where warm, mineral-rich water emerges from below the ocean floor. Enceladus may possess some similar ingredients. Researchers later identified phosphate within salt-rich ice grains from the plume. Phosphorus is essential to life on Earth. It forms part of genetic material, cell membranes, and the molecules used by cells to transfer energy. Further analysis of Cassini data has revealed a broad range of organic compounds and several possible chemical pathways capable of supplying energy. Again, ingredients are not organisms. A kitchen may contain water, heat, carbon, and nutrients without preparing a meal by itself. Chemistry requires particular conditions and histories before it becomes biology. Still, Enceladus gathers many important features within one place: a global ocean, contact with rock, organic chemistry, phosphorus, and available energy. And its ocean is not sealed beyond reach. It continuously sends small samples outward, scattering frozen droplets into the darkness around Saturn. A distant spacecraft has already touched the mist of another world's sea. Titan presents a different kind of possibility. It is Saturn's largest moon, and the only moon in the solar system with a thick atmosphere. Nitrogen dominates that atmosphere, as it does on Earth, while methane helps create a deep orange haze. Beneath the haze lies a landscape shaped by weather. Clouds gather, rain falls, rivers carve channels. Lakes and seas occupy broad depressions near the poles. Rounded stones rest in ancient riverbeds, and dunes stretch across the equatorial regions. Yet Titan's rain is not made primarily from water. Its clouds, rivers, and lakes contain methane and ethane. At Titan's extremely low surface temperature, these substances behave much as water does on Earth. They evaporate, condense, fall as rain, and collect within seas. Titan is the only known world beyond Earth, with stable bodies of liquid openly resting upon its surface. The comparison is both familiar and strange. A shoreline on Titan may resemble a dark terrestrial coast, but its waves move through liquid hydrocarbons. Water ice forms much of the hard ground. Mountains may be built from material that would melt in an earthly kitchen. High in the atmosphere, sunlight and energetic particles break apart methane and nitrogen. Their fragments recombine into increasingly complex organic molecules. These materials drift downward like a fine chemical snow, coating the surface. Titan therefore possesses an enormous natural laboratory for carbon chemistry. Its surface is probably too cold for liquid water-based life to remain active. However, Titan may hide a water ocean beneath its crust. Temporary pockets of melted water could also appear after large impacts. Some researchers have considered whether an entirely unfamiliar kind of biology might use liquid methane rather than water. No evidence shows that such life exists, and no known organism can function that way. The idea remains speculative. Titan's true importance may lie in its resemblance to the chemistry that preceded life on the early Earth. It allows scientists to study how simple atmospheric molecules become complex organic material across an entire world. Beneath the orange haze, chemistry slowly builds structures that biology may someday use, or may never use at all. Together, Mars and the icy moons change the shape of the search. Life was once imagined as something that required an Earth-like planet beneath a sun-like star. The world needed open oceans, gentle continents, and warm daylight. That picture is no longer the only possibility. Ancient Mars shows that a planet can change dramatically. A wet environment can become a cold desert while preserving fragments of its earlier chemistry. Europa shows that oceans can remain hidden beneath ice, warmed by gravity rather than sunlight. Enceladus shows that a tiny moon can contain water, rock, organic molecules, phosphorus, and chemical energy, and can release samples of that environment into space. Titan shows that weather, lakes, and rich carbon chemistry can arise using liquids very different from terrestrial water. None of these worlds provides confirmed proof of extraterrestrial life, but each removes another reason for assuming Earth's environment is the only kind that matters. Water is not confined to Earth. Organic chemistry is not confined to Earth. Energy-rich reactions are not confined to Earth. Long-lived oceans are not confined to Earth. The solar system contains several places where the requirements associated with life gather together. Some existed in the distant past, others may remain active beneath ice today. The discovery of life in even one of these environments would transform every ocean world in the galaxy. It would suggest that whenever water, chemistry, and energy remain together for long enough, biology may sometimes follow. For now, the oceans remain quiet, but they are no longer imaginary. They move beneath the ice of nearby moons, preserving possibilities in the gentle darkness between worlds. The atmosphere of a distant planet can carry a faint record of everything happening below it. Oceans release vapor. Volcanoes add gases from the interior. Sunlight breaks molecules apart and allows new ones to form. If life is present, organisms may also alter the air through breathing, feeding, growing, and decay. Earth's atmosphere is shaped deeply by biology. Plants, algae, and some microbes release oxygen through photosynthesis. Other organisms produce methane. Forests, oceans, soils, and microscopic cells continuously exchange gases with the sky. From a great distance, no single tree or organism would be visible. Yet the combined chemistry of the entire biosphere could leave a planetary signature. Astronomers search for these signatures using spectroscopy. Light may appear white, but it contains a range of wavelengths. When separated, it becomes a spectrum, rather like sunlight passing through a prism and unfolding into a rainbow. Molecules interact with particular wavelengths. Water absorbs certain bands of light. Methane absorbs others. Carbon dioxide, oxygen, ozone, and many additional gases each leave recognizable patterns. These patterns are sometimes called chemical fingerprints. When an exoplanet passes in front of its star, a small amount of starlight travels through the planet's atmosphere before reaching a telescope. Atmospheric molecules remove tiny portions of that light. The missing wavelengths reveal which gases may be present. The signal is remarkably delicate. The star may be millions of times brighter than the faint atmospheric ring surrounding the planet. Clouds can hide deeper layers. Activity on the star can alter the observations. Several molecules may absorb similar wavelengths, making them difficult to distinguish. Astronomers therefore observe multiple transits and compare different instruments. They build computer models containing possible temperatures, clouds, chemical abundances, and atmospheric structures. Gradually, a spectrum becomes a description of an unseen sky. No spacecraft needs to cross the distance. No sample must be carried home. The planet may remain only a dark silhouette against its star, yet a few filtered particles of light can reveal the gases drifting through its atmosphere. Across dozens or hundreds of light years, distant skies quietly write their chemistry into starlight. The first atmospheres studied in detail belong mainly to large, hot planets. These worlds are not considered likely homes for familiar life. Many are gas giants orbiting extremely close to their stars. Their temperatures may become high enough to vaporize metals, while their enormous atmospheres extend far into space. They are useful because they produce strong signals. A large planet blocks more of its star. A broad atmosphere filters more light. Short orbits allow astronomers to observe many transits within a relatively brief period. These worlds became natural classrooms for learning how to read alien skies. WASP 96b is a hot gas giant located more than 1,000 light-years away. It completes an orbit in only a few Earth days. When the James Webb Space Telescope observed one of its transits, the resulting spectrum revealed the presence of water vapor and provided information about clouds and haze. Webb did not photograph individual droplets. Instead, water molecules absorbed specific wavelengths from the starlight passing through the atmosphere. Their presence appeared as a sequence of gentle rises and falls across a graph. WASP 39b offered an even richer chemical portrait. Webb detected carbon dioxide clearly in its atmosphere. Additional observations revealed water vapor, carbon monoxide, sodium, potassium, and sulfur dioxide. The sulfur dioxide was especially important because it is produced through photochemistry. High-energy light from the star initiates reactions within the atmosphere. These reactions transform sulfur-bearing molecules, creating a substance not expected to appear in the same abundance without that interaction. For the first time, astronomers could examine photochemistry occurring on a planet beyond the solar system in such detail. These observations do not provide signs of biology. They demonstrate that the method works. Telescopes can identify several gases at once. They can study temperature, clouds, chemical reactions, and the influence of a distant star. Each hot giant becomes a test of the techniques that may later be applied to smaller and cooler planets. Before astronomers can recognize the subtle atmosphere of another Earth, they must first learn to read clearer and larger signals. The glowing giants close to their suns are teaching them the language of distant air. Rocky planets present a much quieter challenge. A world the size of Earth possesses a thin atmospheric ring compared with a gas giant. During a transit, the additional dimming created by that atmosphere may be only a few parts per million. Clouds can flatten the spectrum. A star's surface may contain cool spots and bright regions that imitate atmospheric signals. Red dwarf stars can produce flares and strong radiation. Their changing surfaces may leave patterns within the same light astronomers are trying to interpret. Even an airless planet can teach something important. Webb observed TRAPPIST-1b, the innermost planet in its 7-world system. Measurements of its heat suggested that it lacks a substantial atmosphere capable of moving warmth efficiently from the day side to the night side. TRAPPIST-1c also appears unlikely to possess the thick carbon dioxide atmosphere once considered possible. These results may seem disappointing, but absence is valuable information. It reveals how close-in rocky planets respond to their stars. It helps researchers improve atmospheric models. It narrows the range of possibilities for the outer and cooler planets within the same system. Another rocky world, 55 Cancri e, offers a different story. This planet is nearly twice Earth's diameter and circles extremely close to a sun-like star. Its surface is hot enough for molten rock to exist. Webb measurements suggest that gases may surround it, possibly released or replenished by a vast ocean of magma. The planet is not a likely home for life. Yet detecting a possible atmosphere around such a small, hot world demonstrates that Webb can investigate gases surrounding rocky planets, rather than only giants. Each observation adds another small skill. Astronomers learn how to separate planetary heat from starlight. They learn how rocks, clouds, and gases shape a spectrum. They learn how much observing time is needed to distinguish a true feature from noise. The search for life is therefore built partly from worlds that may never support it. Their barren surfaces and unusual skies help prepare the instruments for a much more delicate discovery. K218b became one of the most discussed worlds in this search. It orbits a cool red dwarf about 124 light-years from Earth. Its orbit lies within the star's habitable zone, and the planet is approximately 2.6 times Earth's diameter with more than 8 times its mass. This makes it a sub-Neptune. Sub-Neptunes are larger than Earth but smaller than Neptune. They are among the most common planets discovered in the galaxy. Although the solar system contains no direct example, the nature of K2-18b remains uncertain. It may possess a deep hydrogen-rich atmosphere over a high-pressure interior. Some models have proposed that it could be a Hycean world, with a global ocean beneath a hydrogen atmosphere. Other models suggest conditions beneath that atmosphere may be too warm or too pressurized for a familiar ocean. Webb observations detected methane and carbon dioxide in its atmosphere. Water vapor was not securely detected. In 2023, researchers reported a tentative hint of dimethyl sulfide, commonly called DMS. On Earth, much of this gas is linked to marine microorganisms. Additional observations reported in 2025 were interpreted by the same research group as possible evidence for DMS, or the related molecule dimethyl disulfide. The result received widespread attention, but it did not represent proof of life. Other research teams reprocessed the observations using different methods. Their joint analyses found that the evidence for DMS and dimethyl disulfide was not statistically significant. Similar spectral features could be fitted by other molecules, and small choices in data reduction changed the result. A NASA-led analysis also found that instrumental effects and the way wavelengths were grouped could strongly influence the apparent signal. The robust atmospheric findings remained methane and carbon dioxide, not a confirmed biological gas. Work published in 2026 continued to support interpretations of K2-18b that do not require DMS or a water-rich interior. This is how science approaches an extraordinary possibility. One group identifies a pattern. Other groups test the same information independently. Different models compete. Weak signals either grow stronger through repetition or slowly dissolve into better explanations. K2-18b remains deeply interesting. Its atmosphere is real. Its carbon-bearing molecules are real. Its exact environment is still being uncovered. But as of 2026, it does not provide confirmed evidence of extraterrestrial life. The planet has offered something quieter, a demonstration of how carefully the first possible biosignature must be examined. Oxygen may appear to be the clearest gas to seek. Earth's atmosphere contains about 21% oxygen. Nearly all of it is connected, directly or indirectly, to photosynthetic life. Plants, algae, and cyanobacteria use sunlight to separate water and carbon dioxide. They store energy within carbon-rich molecules and release oxygen into their surroundings. Over geological time, that process transformed the planet. An observer studying modern Earth from far away might detect oxygen or its chemical relative, ozone. Either could suggest that a large and active biosphere continuously replenishes the atmosphere. But oxygen alone would not prove life. Ultraviolet light can split water molecules high in a planet's atmosphere. Lightweight hydrogen may escape into space, leaving oxygen behind. Under certain conditions, carbon dioxide can also be separated by starlight, allowing oxygen to accumulate without biology. A planet that has lost an ocean might therefore retain an oxygen-rich atmosphere. It could appear alive while being dry and empty. Scientists search for contextual clues that reveal these false positives. An enormous amount of oxygen may be suspicious. Strong carbon monoxide appearing beside oxygen can indicate that carbon dioxide is being broken apart by radiation. The planet's star also matters. Different stars produce different proportions of ultraviolet light. This changes atmospheric chemistry and affects how quickly oxygen, methane, and other molecules are created or destroyed. Geology matters as well. Fresh volcanic rock can react with oxygen and remove it. Oceans can dissolve gases. A planet's mass controls how easily atmospheric material escapes. Temperature determines whether water remains on the surface or rises into the upper atmosphere. Even biology may exist without producing detectable oxygen. Life occupied Earth for a very long time before oxygen became abundant in the atmosphere. A distant observer examining the young Earth might have missed its biosphere entirely. Oxygen can therefore create both kinds of error. It may appear without life, or life may exist without it. The most convincing discovery will not rest upon a single familiar molecule. It will emerge from the relationship between many gases, the planet and its star. A biosignature is not merely a fingerprint. It is a fingerprint discovered within the full story of the world that carries it. The strongest atmospheric clue may be a mixture that should not remain stable. Earth's atmosphere contains oxygen and methane at the same time. These gases readily react. Left alone, methane would gradually disappear in an oxygen-rich atmosphere. Its continued presence means that something keeps replacing it. On Earth, living organisms provide much of that replacement. This condition is called chemical disequilibrium. An atmosphere in perfect equilibrium has largely settled into stable combinations. A disequilibrium atmosphere contains chemicals that continue existing together, despite their tendency to react. It resembles seeing a warm cup beside an unmelted piece of ice. The arrangement cannot remain unchanged forever. Some continuing process must restore it. Life is one possible process. Earth's biosphere continuously pushes the atmosphere away from simple equilibrium. Photosynthesis supplies oxygen. Microorganisms release methane. Nitrogen-based biology contributes other gases in smaller quantities. A distant telescope might not see the organisms themselves. It might see the chemical tension they maintain. Yet disequilibrium also requires careful interpretation. Volcanoes can resupply reactive gases. Sunlight can drive atmospheric reactions. Impacts, oceans, and interactions between rock and water can maintain unusual combinations. Researchers therefore calculate how much chemical energy is stored within an atmosphere and whether non-living processes could plausibly sustain it. Oxygen together with methane is often discussed as a promising pair. Oxygen with nitrous oxide may offer another. In a hydrogen-rich atmosphere, different combinations could become more meaningful. No universal mixture guarantees biology. The best signal will depend on the kind of planet being observed. A rocky world around a sun-like star requires one set of models. A cooler world around a red dwarf requires another. A young planet with active volcanoes cannot be interpreted in exactly the same way as an old, geologically quiet world. The search is gradually moving beyond a list of individual gases. Scientists are looking for whole atmospheric systems that appear to be maintained by an active surface. Life may not announce itself with one molecule. It may reveal itself through a planet that refuses to become chemically still. A living world might also change with its seasons. Earth does not present the same atmosphere throughout the year. In the northern hemisphere's spring and summer, plants absorb more carbon dioxide. During autumn and winter, some of that carbon returns to the air. Oxygen also follows a subtle seasonal rhythm. The change is small, but it reflects the breathing of forests and oceans across an entire hemisphere. A distant civilization observing Earth with sufficiently precise instruments might notice these repeating patterns. Gas levels would rise and fall with the planet's orbit around the Sun. Seasonal variations could become an additional biosignature. They would not depend upon one measurement. They would repeat in time, linked to changing sunlight, temperature, and biological activity. Non-living planets also experience seasons. Carbon dioxide freezes and evaporates at the poles of Mars. Clouds form and fade. Photochemical reactions vary as a world moves through an eccentric orbit. Geological activity can release gases irregularly. The timing and relationships between changes would therefore matter. A biological seasonal cycle might involve several gases shifting together. It might repeat steadily over many planetary years. Its pattern would need to match plausible responses from organisms to light and warmth. The surface could add further clues. Vegetation on Earth reflects near-infrared light strongly because leaves must release excess solar energy. This creates a feature known as the vegetation red edge. A sufficiently advanced telescope might someday detect a broad change in the reflected light of a distant planet. Alien photosynthesis may not use green pigments. Life under another star could absorb different wavelengths. Its forests, microbial mats, or floating organisms might appear dark violet, orange, red, or nearly black. Researchers therefore avoid searching only for an exact copy of Earth's green surface. They study more general patterns, unusual reflectivity, pigments adapted to a star's light, and surface changes that move with the seasons. Atmospheric gases may offer the first clue. Repeated planetary rhythms could provide the next. A distant living world might not send a message. It might simply brighten, darken, and exchange gases as it moves quietly around its sun. The examination of distant atmospheres has not yet produced proof that humanity is not alone. It has achieved something that would have seemed almost impossible a generation ago. Astronomers can measure water, carbon dioxide, methane, sulfur dioxide, and other gases on planets that cannot be seen as more than points or shadows. They can estimate temperatures, identify clouds, observe photochemistry, and test whether rocky worlds retain their air. The technique remains young. Current telescopes are often better suited to large planets with extended atmospheres. Signals from small temperate worlds demand repeated observations and exceptional control of noise. Future observatories are being designed with these worlds in mind. They may separate the weak reflected light of an Earth-sized planet from the brilliance of its star. They may search broad wavelength ranges for oceans, clouds, oxygen, methane, surface pigments, and chemical disequilibrium. No single observation will likely provide the entire answer. Confidence may build slowly. First comes evidence that a planet is rocky, then evidence of an atmosphere, then moderate temperatures, water, and several unusual gases. Later observations may reveal seasons or surface patterns. Independent teams may test the result with different instruments. The first convincing proof may therefore arrive not as one dramatic moment, but as a structure assembled from many quiet measurements. A shadow passes before a star, a spectrum forms, several small gaps appear in the light, and within those missing colors, another living world may eventually become visible. Life does not need to alter a planet's atmosphere to reveal itself. A technological civilization may produce signals and structures that nature rarely creates. Radio transmitters can send energy across interstellar distances. Lasers can form brief flashes of concentrated light. Large machines may change the infrared glow of a planetary system. Industrial chemistry might introduce unusual compounds into an atmosphere. Scientists call these possible signs technosignatures. A biosignature points toward biological activity. A technosignature points toward technology created by living intelligence. Either could provide the first confirmed evidence that life exists beyond Earth. Technosignatures do not require another civilization to contact humanity deliberately. A distant society might use powerful radar to study objects within its own system. Its communication beams might occasionally pass across Earth. Energy collectors could release heat that telescopes detect from far away. Industrial gases might gather in an atmosphere even when no message is being transmitted. Humanity already produces several technosignatures of its own. Earth is surrounded by radio emissions from satellites, radar installations, television systems, and deep space communication networks. Cities create artificial light on the planet's night side. Spacecraft move between worlds. Chemicals manufactured by industry appear within the atmosphere. Most of these signatures become faint over interstellar distances. However, some powerful radar transmissions could be detected much farther away than ordinary radio leakage. A sufficiently sensitive telescope aimed toward Earth at the right moment might recognize that the planet produces organized technology. This changes the search in an important way. Scientists are not only looking for creatures resembling humans, they are searching for energy arranged in ways that ordinary stars, planets, and clouds do not easily explain. The civilization responsible could be ancient or young. Its technology could resemble radio instruments, or it could operate through methods not yet imagined on Earth. Technosignature research therefore begins with familiar physics while remaining open to unfamiliar possibilities. No confirmed technosignature has yet been discovered, but the search now extends across radio waves, visible light, infrared radiation, atmospheric chemistry, and enormous astronomical databases. Intelligence may not leave footprints upon the soil of Earth. It may leave a small pattern within the light arriving from the stars. Radio waves remain among the most practical ways to search for distant intelligence. They travel at the speed of light and can cross enormous regions of space. Earth's atmosphere allows many radio frequencies to reach the ground, where large observatories can collect them. Natural objects also produce radio waves. Stars release radio emission. Jupiter generates powerful bursts. Pulsars send rhythmic beams across the galaxy. Gas clouds, black holes, and exploding stars contribute their own signals to the cosmic background. The challenge is to identify a pattern that appears engineered rather than natural. One promising target is a narrowband signal. Natural radio sources usually spread their energy across a wide range of frequencies. A deliberately constructed transmitter can concentrate energy into a very narrow channel. This allows information to travel efficiently and makes the signal easier to distinguish from broad natural emission. A narrow line within the radio spectrum would not automatically prove technology. Human equipment produces countless narrowband signals. Satellites, aircraft, mobile networks, navigation systems, observatory electronics, and nearby transmitters can all enter astronomical data. The sky above a radio telescope is never completely quiet. Scientists must therefore separate a signal arriving from a distant star from one produced somewhere near Earth. They examine its frequency, strength, duration, direction, and movement through the spectrum. A true interstellar transmitter would probably appear to drift slightly in frequency. The transmitter's planet would rotate. It would also orbit its star. Earth rotates and orbits the Sun at the same time. These motions change the relative velocity between sender and receiver. The result is a gentle Doppler shift. The signal may slide slowly upward or downward in frequency while it is observed. Searching for this drift allows computers to identify patterns consistent with transmitters located on moving worlds. Modern radio telescopes divide incoming signals into millions or billions of narrow-frequency channels. Automated systems examine these channels for unusual lines and drifting features. Most are created by human technology. A small number survive the first filters and receive closer attention. Within a vast sea of radio noise, the search begins by looking for one quiet line that behaves as though it belongs to another moving world. A promising signal must also follow the telescope's movement across the sky. Researchers often observe a target star and then point the telescope toward a nearby empty region. They later return to the star and repeat the sequence. This is sometimes called an on-off observation pattern. A signal associated with the target should appear while the telescope points toward the star. It should disappear when the telescope moves away. It should return when the telescope points back. Local interference behaves differently. A signal from a satellite or ground-based transmitter may remain visible no matter where the telescope points. It may appear across several directions or return irregularly as equipment moves above the horizon. This simple comparison removes many false candidates. The surviving signals then face further tests. Scientists examine whether the signal repeats. They search other observations taken at different times. They compare information from independent telescopes. They investigate whether the frequency overlaps with known satellites or communication systems. Repetition is especially important. A single unusual signal can arise from an instrument, a brief natural event, or interference that may never occur in exactly the same way again. A repeating signal from the same location would allow astronomers to study it carefully and rule out ordinary explanations. Confirmation would ideally involve another observatory. A second telescope located far away would experience a different environment of local interference. If both observatories detected the same signal from the same region of the sky, confidence would rise. The signal would still require patience. Its encoded information might not be immediately understandable. It might be a simple beacon rather than a message. It could repeat only once during a long planetary rotation, or appear when a narrow beam happened to cross Earth. Radio SETI is therefore less like waiting beside a telephone, and more like listening across an enormous ocean. The receiver samples one direction, one range of frequencies, and one period of time. Then it moves elsewhere. Most places are quiet. Some contain human interference. A genuine discovery would be the signal that continues following the star after every nearby explanation has gently fallen away. Breakthrough. Listen greatly expanded the scale of this search. The program uses powerful observatories to examine nearby stars, the plane and center of the Milky Way, and galaxies beyond it. Its long-term goals include surveying 1 million nearby stars and 100 neighboring galaxies across wide portions of the radio and optical spectrum. These numbers sound enormous, yet even a search of 1 million stars samples only a small fraction of the Milky Way. The galaxy contains hundreds of billions of stars, many surrounded by planets. Each target must also be observed across many possible frequencies. A civilization could transmit at a low radio frequency or a much higher one. Its signal might be continuous, periodic, or present only for a few seconds. It might be directed narrowly toward another planet, rather than broadcast in every direction. Time creates another dimension. A telescope may study a star for several minutes while the transmitter remains silent. A beacon might operate once every month. A civilization may have used radio centuries ago, and later changed its technology. The search space is not merely the sky. It includes direction, frequency, bandwidth, signal shape, repetition, polarization, transmission power, and time. Breakthrough Listen collects immense volumes of data because each observation contains millions of channels. Software searches for narrowband lines, pulses, and patterns that drift as expected from a distant moving source. Machine learning systems are also helping identify signals that older methods may overlook. One deep learning search examined observations of hundreds of nearby stars. It found several signals of interest that had not been selected by earlier algorithms. Follow-up observations did not detect them again, so they did not meet the requirements for technosignature candidates. That result was still useful. It demonstrated that new methods can search old information differently. A future discovery may already be resting unnoticed within a stored dataset, waiting for a more sensitive algorithm. Radio observatories collect more than signals. They collect possibilities. Every improvement in computing allows the same quiet sky to be examined again with sharper attention. One of the most instructive candidates appeared during observations of Proxima Centauri. Proxima is the nearest star beyond the Sun. It lies only about 4.2 light-years away and hosts at least one confirmed planet within its traditional habitable zone. In 2019, the Parkes Radio Telescope in Australia observed the system as part of a study of stellar activity. Later analysis revealed a narrowband signal near 982 MHz. The signal became known as Breakthrough Listen Candidate 1, or BLC1. Several characteristics made it interesting. It occupied a narrow frequency range. It appeared to drift gradually. It was present during multiple observations aimed toward Proxima and initially seemed absent from some observations pointed elsewhere. These were features expected from a possible transmitter located beyond Earth. Researchers did not announce a discovery. They began a detailed investigation. The team searched a much larger collection of observations and found signals resembling BLC1 at other frequencies. These related patterns suggested that BLC1 belonged to a family of interference created by human equipment. The most likely explanation involved intermodulation. Electronic systems can combine several ordinary frequencies and produce additional signals. These products may appear narrow, drifting, and isolated. Under unusual conditions, one can imitate the features expected from a distant transmitter. Follow-up observations of Proxima Centauri did not detect BLC1 again. The candidate was eventually classified as radio frequency interference rather than evidence of extraterrestrial technology. Yet the episode became valuable. Researchers published their methods and showed how a candidate moves through the verification process. BLC1 survived enough tests to receive exceptional scrutiny. It then failed when broader evidence revealed related human-made signals. The story illustrates the strength of a careful search. Scientists wanted to discover something extraordinary, but they worked equally hard to disprove it. The signal remained interesting only while ordinary explanations were insufficient. BLC1 did not open communication with another world. It showed that the search had developed tools capable of taking a faint possibility seriously and then letting it go when the evidence changed. The most famous unexplained radio event remains the WOW signal. On August 15, 1977, Ohio State University's Big Ear radio telescope recorded an unusually strong narrowband signal. It lasted for about 72 seconds, matching the length of time that a fixed point in the sky passed through the telescope's observing beam. Astronomer Jerry Amon later examined the printed data. He circled the sequence describing the signal's intensity and wrote the word WOW beside it. The small handwritten reaction became the signal's permanent name. The observation stood close to the frequency associated with neutral hydrogen. Hydrogen is the most common element in the universe. Some early SETI researchers considered its natural radio frequency a possible meeting place where an unfamiliar civilization might choose to transmit. The signal's rise and fall also resembled the pattern expected from a fixed celestial source moving through the Big Ear telescope's beam. But it appeared only once. Repeated searches of the same region failed to detect it again. Big Ear used 2 observing beams, and the signal appeared in only one. Its precise origin could not be identified. Many explanations have been proposed. Some involve human interference. Others involve natural hydrogen clouds, stellar activity, comets, or rare astronomical events. Later studies have offered possible natural mechanisms, but none has achieved universal confirmation. The WOW signal therefore remains unexplained. Unexplained does not mean extraterrestrial. It means the surviving information is insufficient to select one answer confidently. The original observation was brief, and no second telescope recorded it. Modern instruments cannot return to the past and measure additional properties. A repeating signal could be tested. The WOW signal remains a single page from a story whose other pages were never collected. Its importance lies partly in the lesson it preserves. An unusual observation can remain genuinely interesting for decades without becoming proof. Scientific uncertainty is not a hidden confirmation. It is simply the honest boundary between what the evidence shows and what imagination can add. The signal arrived, rose gently, faded, and never returned. Its source remains somewhere between Earth, the stars, and the limits of one old telescope's memory. Nature has repeatedly shown that it can imitate the rhythm of technology. In 1967, graduate student Jocelyn Bell Burnell noticed a radio source producing remarkably regular pulses. The pulses repeated so precisely that the research team briefly considered whether they might come from intelligent transmitters. The source received the playful nickname LGM-1, meaning Little Green Men. Additional sources soon appeared in other parts of the sky. It became clear that the signals belonged to a new kind of natural object. They came from rapidly rotating neutron stars, now known as pulsars. A neutron star forms when a massive star reaches the end of its life and its central region collapses. The remaining object contains more mass than the Sun compressed into a sphere, roughly the size of a city. Some neutron stars rotate many times every second. Their magnetic fields guide beams of radiation outward. When a beam sweeps across Earth, telescopes detect a pulse. The effect resembles the repeating flash of a distant lighthouse. Pulsars became valuable cosmic clocks. Their regularity helps astronomers test gravity, study interstellar material, and search for gravitational waves. The signals that briefly suggested technology instead revealed a new state of matter. Fast radio bursts offer another example. These brief events release powerful pulses of radio energy, often from galaxies far beyond the Milky Way. Some sources repeat, while others have been observed only once. Their sudden appearance once inspired speculation about artificial origins. Evidence now connects at least some fast radio bursts to magnetars, highly magnetized neutron stars. In 2020, observatories detected a fast radio burst from a magnetar inside the Milky Way, alongside high-energy emission. This did not necessarily explain every fast radio burst. It demonstrated that nature possesses a mechanism capable of producing them. The history of pulsars and fast radio bursts encourages patience. The universe creates patterns that can appear deliberate before their physical mechanisms are understood. A signal's strangeness is a reason to study it. It is not by itself evidence of intelligence. Sometimes the most unfamiliar voice in the radio sky belongs not to a civilization, but to a star revealing a form of nature that science had never heard before. Intelligent signals may also arrive as flashes of visible or infrared light. A powerful laser can concentrate energy into a narrow beam. For a brief moment, such a pulse could outshine the host star at one specific wavelength. An advanced civilization might use lasers for communication between planets or stars. Light could also contribute to propulsion systems that push thin sails across space. Optical SETI searches for these possibilities. Some programs examine stellar spectra for narrow emission lines that do not match known chemistry. Others use fast detectors to search for pulses lasting only billionths of a second. The pulse may appear in several nearby telescopes at the same moment. This helps distinguish a celestial flash from particles striking one detector or lights moving through Earth's atmosphere. Laser searches offer certain advantages. Optical telescopes can determine the source direction precisely. Large amounts of information can be carried by short pulses. A directed beam may remain detectable across great distances if it happens to point toward Earth. The same narrowness creates a limitation. A beam aimed toward another destination would pass unseen. Even a powerful civilization may illuminate only a tiny part of the sky at any moment. Humanity would need to be located along the beam's path at exactly the right time. Programs associated with Breakthrough Listen and the SETI Institute now combine radio and optical approaches. Laser SETI, for example, is designed to monitor broad regions for brief optical flashes rather than studying only one star at a time. No confirmed extraterrestrial laser has been detected, but optical searches expand the range of technologies that telescopes can recognize. A civilization may not use radio in the way current assumptions expect. It may prefer tightly directed light. The first technological signal could therefore be silent to a radio receiver. It might arrive instead as a tiny flash, crossing the darkness in less time than an eye can blink. Some technosignatures may be found without detecting a message at all. Every technology that uses energy must eventually release heat. A machine can transform energy into motion, computation, communication, or construction. Yet some energy becomes disordered thermal radiation and escapes into the surrounding environment. Human cities release waste heat. Computers warm their rooms. Engines warm the air. Even solar panels eventually return absorbed energy to the environment as infrared radiation. The same physical principle would apply to technology elsewhere. A civilization using a large fraction of its star's energy might build vast collections of orbiting energy collectors. The complete shell often imagined around a star is known as a Dyson sphere, although a more realistic arrangement could be a broad swarm of separate structures. Such technology could partially block visible starlight. After using the collected energy, it would release waste heat at longer infrared wavelengths. A star surrounded by large amounts of machinery might therefore appear dimmer in visible light and unusually bright in infrared. Astronomers can search existing sky surveys for this imbalance. Most unusual infrared objects eventually receive natural explanations. Dust surrounding young or aging stars also absorbs visible light and re-radiates it as heat. Galaxies contain warm clouds, forming stars and active central black holes. A convincing candidate would need to differ from these familiar systems. Its temperature, spectrum, variability, and surrounding environment would all require study. Researchers might look for a star with excessive infrared radiation, but little evidence of the dust that normally produces it. Technology could also influence a planet's atmosphere. Industrial activity may produce molecules that are rare in natural environments. Certain manufactured gases absorb infrared light strongly and can persist for long periods. Future telescopes might search for such chemicals on nearby exoplanets. Again, no single unusual feature would be enough. Unknown geology or chemistry could create surprises. Every possible technosignature must be compared with natural explanations. The search nevertheless reaches beyond deliberate communication. A civilization may never call across the stars. Its use of energy could quietly reshape the light of its world. The absence of a confirmed signal does not show that technological life is absent. Humanity has searched only a small portion of the possible cosmic landscape. A useful comparison imagines the entire search space as Earth's oceans. Every frequency, direction, moment, signal type, and sensitivity level adds another volume of water. Present searches have sampled only scattered cups. A radio telescope may observe one star for several minutes. That star may host no civilization. A civilization may be present but silent. It may transmit on another frequency, in another direction, or during another century. Its signal may be too weak for current instruments. It may use communication methods unknown to present physics and engineering. Its active technological period may have ended millions of years before humanity appeared. Distance also carries time. A signal from a world 1,000 light-years away began its journey 1,000 years ago. Telescopes do not observe that civilization as it exists now. They observe a fragment of its past. The Milky Way contains stars of many ages. Some planetary systems formed billions of years before the solar system. Others are only beginning. Intelligence, if it arises, may appear at widely separated moments. Two civilizations could inhabit the same galaxy and remain separated not only by distance but by time. Searches are gradually becoming broader. New receivers examine larger frequency ranges. Arrays can observe many stars at once. Artificial intelligence can filter enormous datasets. Optical instruments monitor broad areas for brief flashes. Infrared surveys search for unusual heat. Each improvement collects another small cup from the cosmic ocean. None has yet contained confirmed evidence of another intelligence, but the ocean itself remains almost entirely unexamined. The silence heard so far is real. Its meaning is not yet known. It may reflect rarity, distance, timing, unfamiliar technology, or simply the smallness of the search. For now, the quiet sky does not provide proof that humanity is alone. It provides room for the listening to continue. Life on Earth occupies a much wider range of environments than anyone once expected. For much of human history, living things seemed closely tied to familiar conditions. They needed mild temperatures, clean water, breathable air, and sunlight arriving from above. These requirements describe human life well. They do not describe all life. Microorganisms flourish in boiling springs, concentrated salt water, acidic pools, frozen soil, deep rock, and places exposed to intense radiation. Some live without oxygen, others remain active beneath enormous pressure. Entire ecosystems exist in permanent darkness, supported by chemical energy rather than sunlight. These organisms are often called extremophiles. The word describes life that thrives under conditions humans consider extreme, but the organisms themselves do not experience their environments as unusual. Their cells have been shaped by evolution to function there. Some proteins remain stable at temperatures that would damage ordinary cells. Certain microbes maintain internal chemistry, despite living in highly acidic water. Salt-loving organisms keep their proteins working, while surrounded by concentrations that would pull water from most cells. Cold-adapted life produces flexible molecules that continue functioning when chemical reactions become slow. Radiation-resistant organisms possess powerful systems for protecting and repairing genetic material. Each adaptation expands the known boundaries of biology. Extremophiles do not prove that life exists elsewhere. Every organism studied on Earth belongs to the same broad family of terrestrial life. They share genetic chemistry and descend from ancient ancestors that lived on this planet. Yet they reveal something important. Earth-like life is not restricted to Earth-like comfort. Once biology begins, evolution can guide it into places that appear empty from a human perspective. Heat, cold, darkness, pressure, acidity, salt, and radiation may limit life without always eliminating it. This discovery changes how other worlds are examined. A cold Martian desert may still contain protected spaces underground. Europa's dark ocean may still offer energy. Enceladus may not need sunlight if water reacts with rock along its seafloor. The environments considered habitable have widened because life on Earth repeatedly crossed boundaries that once seemed final. The planet's smallest inhabitants have quietly redrawn the map of where living chemistry can endure. Hydrothermal vents provided one of the great changes in this understanding. Deep beneath the ocean, seawater enters cracks in the crust. It descends toward hot rock, absorbs dissolved minerals, and rises again through openings on the seafloor. Some vent fluids exceed 300 degrees Celsius. The immense pressure of the deep ocean prevents the water from immediately boiling. When the hot fluid meets cold seawater, minerals form dark clouds and slowly build tall structures around the opening. No sunlight reaches these depths. For a long time, scientists assumed that deep-sea ecosystems depended almost entirely on organic material drifting down from the bright surface. Yet expeditions discovered dense communities surrounding hydrothermal vents. Tubeworms, clams, mussels, crabs, shrimp, and many smaller creatures gather near the flowing water. At the foundation of these communities are microorganisms. Instead of capturing light, these microbes obtain energy from chemical reactions. They use substances such as hydrogen sulfide, hydrogen, methane, or iron compounds. The process is known as chemosynthesis. Chemosynthetic microbes turn inorganic chemicals into organic matter. Other organisms feed upon them or live in partnership with them. Giant tubeworms, for example, contain internal bacteria that provide much of their nourishment. A food web develops in complete darkness. The existence of these ecosystems separates life from direct sunlight. Energy still remains essential, but it can arrive through geology rather than from a star. This has profound implications for ocean worlds. Europa and Enceladus may contain rocky seafloors beneath their hidden oceans. If liquid water circulates through warm rock, chemical gradients could form. These gradients might supply energy in ways loosely comparable to terrestrial vents. No vent has yet been directly observed on Europa. Evidence from Enceladus suggests that warm water interacts with rock inside the moon. Cassini detected silica particles and molecular hydrogen in material released from its ocean, both consistent with hydrothermal processes. The analogy must remain careful. An alien seafloor may differ greatly from Earth's. Its chemistry, temperature, pressure, and history may not support biology. But hydrothermal vents demonstrate that a dark ocean is not automatically a lifeless ocean. Where water and rock exchange energy, a world can possess an unseen foundation for living systems. Hot springs reveal another landscape where chemistry and life meet. Geothermal water rises from beneath the ground, carrying dissolved minerals and heat. Some springs are gently warm, others approach temperatures near the known limits of cellular activity. Their colors can appear almost painted. Green, orange, yellow, and brown microbial communities form bands across the water and surrounding rock. Each band may represent organisms adapted to a different combination of temperature, light, oxygen, and chemistry. The arrangement forms a living thermometer. Photosynthetic microbes can occupy cooler edges where sunlight reaches them. Organisms adapted to greater heat live nearer the source. Some archaea flourish in hot and acidic conditions where most cells would quickly break down. High temperature creates several challenges. Heat can unfold proteins, disrupting the shapes they need to function. It can weaken cell membranes and damage genetic molecules. Thermophiles possess proteins with structures that remain stable under these conditions. Their membranes contain chemical features that help prevent them from falling apart. Repair systems correct damage as it occurs. Cold creates the opposite problem. Molecules move more slowly. Membranes become rigid. Ice can remove liquid water and create sharp changes in salt concentration. Cold-adapted organisms use flexible enzymes and membrane compounds that remain functional at low temperatures. Some produce substances that reduce ice damage. Others survive inside tiny films of liquid water between ice crystals or within salty droplets that remain unfrozen. These adaptations matter beyond Earth because temperature is rarely uniform across an entire world. A planet may appear frozen while maintaining warmer places below its surface. A volcanic region may contain narrow zones where heat and water overlap. Ice may contain microscopic liquid pockets even when the surrounding landscape remains solid. Habitability can exist within small gradients. It does not always cover continents or open oceans. A single crack, mineral pore, or thin boundary between hot and cold material may contain conditions unavailable across the wider environment. Life on Earth often gathers within these boundaries. It occupies the gentle middle between extremes, even when that middle is only a few millimeters wide. Salt, acidity, dryness, and radiation each reveal another kind of endurance. Highly salty water creates pressure across a cell membrane. Water naturally moves toward the saltier environment, which can leave an ordinary cell dehydrated. Halophiles solve this problem in several ways. Some accumulate compatible molecules inside themselves, balancing the surrounding salt without disrupting their chemistry. Others maintain high internal concentrations of potassium and possess proteins specifically adapted to salty conditions. These organisms inhabit salt lakes, evaporation ponds, and crystals of salt. Their existence is relevant to Mars, where liquid water near the surface may be rare and temporary. Salts can lower water's freezing point, allowing briny films or droplets to remain liquid under conditions where pure water would freeze. Acid-loving organisms provide another example. Certain microbes live at acidity levels approaching those of battery acid. They maintain a far more neutral interior by controlling the movement of charged particles across their membranes. Other organisms thrive in strongly alkaline water. Life can therefore preserve its internal environment, even while the chemistry outside it differs greatly. Dryness presents a slower challenge. Without water, most metabolism stops. Some organisms enter dormant states, reducing activity until moisture returns. Spores can protect genetic material and essential cellular structures for long periods. Radiation can break chemical bonds and fragment DNA. Several microorganisms survive unusually high doses because their cells limit damage and rebuild genetic material efficiently. Survival does not make them immune, and radiation remains a serious boundary. Yet that boundary lies farther outward than early biology expected. The Atacama Desert, Antarctic valleys, high-altitude air, and radiation-rich environments serve as analogues for conditions beyond Earth. Researchers study how organisms survive there, and which biological traces remain after cells become inactive. Sometimes the most important finding is not a living cell. It is a pigment, lipid, mineral pattern, or fragment of organic chemistry preserved after life has disappeared. A rover may arrive long after an environment ceased being habitable. The search must therefore recognize both present organisms and the quiet remains of earlier ones. Extremophiles teach researchers where life might persist. They also teach them what life may leave behind. Some of Earth's largest habitats are hidden beneath its surface. Microorganisms live within cracks, pores, sediments, and groundwater far below the reach of sunlight. They may grow slowly because nutrients and energy are limited. A single generation can require far longer than it would near the surface. These communities form part of the deep biosphere. Some subsurface organisms depend indirectly on material that originally came from photosynthesis. Organic matter may become buried in sediment and remain available for millions of years. Others rely upon chemistry generated within rock. One remarkable community was discovered roughly 2.8 kilometers underground in a South African gold mine. Its dominant organism, Desulforudis audaxviata, lives without direct support from sunlight. Radioactive elements in the surrounding rock slowly split water molecules. This process produces hydrogen. Reactions also generate sulfate compounds. The microorganisms use hydrogen and sulfate within their metabolism. The energy source begins with the slow decay of minerals rather than sunlight reaching the surface. Rock, water, and radioactivity maintain an isolated ecosystem. The process is extremely gentle. No bright starbeam enters the habitat. No forest grows above it. Energy arrives through transformations occurring atom by atom inside ancient stone. Such communities suggest a way life could survive on a planet whose surface has become difficult. Early Mars once possessed rivers and lakes. If life began during that wetter period, some organisms might have moved underground as surface water disappeared and radiation increased. Subsurface rock offers protection. Temperatures become more stable. Ice or groundwater may remain available. Radiation from space weakens with depth. Chemical reactions between water and minerals may provide energy. No underground Martian organism has been detected. Drilling deeply on another planet is technically difficult, and current rovers examine only shallow layers. The possibility remains open rather than demonstrated. The deep biosphere nevertheless changes the meaning of a quiet surface. A world may lose its oceans, atmosphere, and mild climate while retaining protected habitats below. Surface observations alone may not reveal the full extent of its habitability. Earth itself contains a dark biological realm hidden beneath landscapes that appear ordinary. Life does not always cover a world where telescopes can see it. Sometimes it settles into the stone and continues almost invisibly. The durability of microorganisms also creates a responsibility for exploration. Spacecraft assembled on Earth are not automatically free from life. They are built in clean rooms where air filtration, protective clothing, careful cleaning, and sterilization reduce contamination. Even there, some microorganisms remain. The most persistent species may tolerate drying, chemical cleaning, radiation, or limited nutrients. Their survival does not mean they can grow freely on another world, but it means spacecraft must be treated carefully. NASA and other space agencies follow planetary protection procedures. Forward contamination occurs when terrestrial material is carried to another world. A microbe arriving on Mars could confuse future experiments. Researchers might detect Earth life and mistake it for a Martian organism. Contamination could also disrupt an alien environment if life already exists there. Backward contamination concerns material returned to Earth. Samples from potentially habitable worlds require containment and careful examination before their safety is understood. Studies expose microbes to combinations of ultraviolet light, vacuum, drying, radiation, and temperature changes. Balloon experiments carry organisms into Earth's stratosphere, where conditions resemble parts of the Martian surface in limited ways. Some dormant bacteria and fungal spores survive portions of these tests. Survival during an experiment is not the same as reproduction on Mars. A cell may endure briefly and then remain inactive. The Martian surface combines intense radiation, cold, dryness, reactive chemistry, and extremely low pressure. Still, the persistence of terrestrial microbes shows that biology can sometimes travel farther than expected. This connects to the idea of panspermia. Panspermia proposes that life, or its durable precursors, might move naturally between worlds inside rocks ejected by impacts. Martian meteorites have reached Earth, proving that stone can travel from one planet to another. Whether living organisms could survive the complete journey remains uncertain. They would need to endure the impact that launched the rock, years or millions of years in space, and the heat of atmospheric entry. Organisms buried inside a sufficiently large rock might receive some protection from radiation and temperature extremes. Even successful transfer would not explain how life originally began. It would only move the location of its origin. For now, panspermia remains a possibility rather than proof. Planetary protection treats biological travel seriously because even a small chance of contamination matters. The spacecraft searching for alien life must first make certain that the life they find did not travel with them from home. Life's building materials appear far beyond Earth. Carbon forms bonds with many elements and can create an extraordinary variety of molecules. In space, carbon chemistry occurs within cold interstellar clouds, warm regions around young stars, comets, asteroids, and planetary atmospheres. These molecules are organic because they contain carbon. The word does not mean that organisms created them. Some of the clearest evidence comes from meteorites. Carbon-rich meteorites have delivered amino acids and other organic compounds to Earth. Their chemistry shows that important biological ingredients can form without biology. The asteroid Bennu has provided an especially clean example. NASA's OSIRIS-REx spacecraft collected material directly from Bennu and returned it to Earth in 2023. Because the sample was protected from ordinary terrestrial exposure, scientists can examine its chemistry with greater confidence than material that fell through the atmosphere and rested on the ground. Analyzers announced in 2025 identified 14 of the 20 amino acids used by terrestrial life to build proteins. The samples also contained all 5 nucleobases used in DNA and RNA. Researchers found ammonia and other compounds relevant to prebiotic chemistry. Later analysis identified the sugars ribose and glucose. Ribose forms part of RNA's structural backbone. Together with nucleobases and phosphate already found in Bennu material, it completes the basic categories of components needed to construct RNA molecules. This does not mean RNA or life existed on Bennu. The ingredients were not arranged into living cells. The asteroid shows that the chemistry preceding life can develop inside small planetary bodies. Bennu's amino acids also appeared as roughly equal mixtures of left and right-handed forms. Earth life uses almost exclusively left-handed amino acids in proteins. The difference supports a non-biological origin for the asteroid's molecules. It also deepens a question about Earth. If early material arrived with both molecular orientations, some later process caused terrestrial biology to favor one. The reason remains uncertain. Asteroids may have delivered water and organic compounds to the young Earth. Similar deliveries probably occurred on many rocky planets. The materials used by biology are therefore not rare possessions manufactured only after life begins. They appear naturally within the quiet chemistry of planetary systems. The discovery of ingredients must remain separate from the discovery of life. Amino acids do not reproduce. Nucleobases do not maintain a metabolism. Sugars and phosphates do not form an organism simply by resting beside one another. Life requires organization. A living system must separate itself from its surroundings while still exchanging matter and energy. It must preserve information, copy that information with enough accuracy to continue, and allow enough variation for evolution. How non-living chemistry first crossed this boundary remains one of science's deepest questions. Several possibilities are being explored. Life may have begun near hydrothermal vents, where mineral surfaces and chemical gradients provided energy. It may have emerged in shallow ponds that repeatedly dried and refilled, concentrating molecules and encouraging them to join into longer chains. Ice may have protected delicate compounds while concentrating them into liquid channels. Clay minerals may have acted as surfaces upon which molecules assembled. Early Earth may have contained several of these environments at once. Experiments have produced amino acids, nucleobases, membrane-like bubbles, and portions of self-copying chemical systems under plausible early Earth conditions. No experiment has yet recreated the complete transition from simple chemistry to an independently evolving cell. The missing history is difficult to recover because Earth constantly renews its surface. Plate tectonics, erosion, water, heat, and life itself have altered rocks from the planet's earliest period. The first organisms may also have been much simpler than any cell alive today. Their traces may have disappeared long ago. This uncertainty affects estimates of life elsewhere. If the origin of life requires an extremely improbable sequence, then habitable worlds may remain empty. If living chemistry emerges readily whenever water, energy, and suitable molecules persist together, then biology may be common. Earth currently provides only one confirmed example. One example cannot reveal the probability. A second independent origin would change everything. Life found on Mars, Europa, or Enceladus might share chemistry with Earth because material traveled between worlds. But if it used a different genetic system, different molecular handedness, or a clearly independent biochemical structure, it would show that life began more than once. The universe would then contain not merely one spreading tree of life, but at least two separate seeds. The difference between ingredients and organisms remains enormous. Yet the ingredients appear almost everywhere science has learned to look. Extremophiles are not proof that alien life exists. They offer a different kind of evidence. They demonstrate that biology is adaptable after it begins. They show that sunlight is only one possible energy source. They reveal that liquid water can remain useful within ice, rock, salt, and narrow microscopic spaces. They show that life can become slow. A biosphere does not need to cover a planet with forests or alter its clouds visibly. It may consist of sparse cells dividing within stone over immense periods. They also reveal that habitability is local. A world broadly described as frozen, dry, acidic, or irradiated can still contain protected regions where conditions are softer. At the same time, asteroids and meteorites reveal that prebiotic chemistry is not confined to Earth. Amino acids, nucleobases, sugars, and other carbon compounds can form before biology exists. Two quiet lessons therefore meet. The universe naturally produces many of life's materials, and once life exists, it can enter environments that once seemed unreachable. The unknown step lies between them. No observation yet shows how often scattered chemistry awakens into an evolving system. It may happen easily, under the right conditions. It may require a rare sequence repeated on almost no other world. Future exploration will test these possibilities. Mars samples may preserve ancient organic patterns. Europa Clipper will examine whether Jupiter's icy moon possesses environments capable of supporting life. Future missions may pass again through the plume of Enceladus and search for more complex molecular structures. Telescopes will study distant atmospheres. Laboratories will continue building portions of early chemistry. Deep mines, deserts, glaciers, hot springs, and ocean floors will reveal new ways terrestrial organisms survive. The search beyond Earth is partly a search within Earth. Every unusual organism discovered here becomes another possibility elsewhere. Every hidden ecosystem adds a new kind of habitat to the cosmic map. Nothing in these discoveries confirms that another biosphere exists, but they steadily weaken the old assumption that life requires one narrow copy of the surface environment familiar to humanity. The universe offers water in darkness, chemistry inside stone, and organic molecules within ancient asteroids. Earth shows that life can use such quiet opportunities. Whether it has done so elsewhere remains unanswered. The places where the answer could be waiting are no longer few. The size of the universe does not prove that life exists elsewhere, but it changes how the possibility feels. The Milky Way contains at least 100 billion planets, and some estimates suggest far more. Beyond the Milky Way lie hundreds of billions of other galaxies, each containing stars, dust, gas, and planetary systems of its own. Only a small fraction of these worlds needs to offer suitable conditions for the number of possible habitats to become immense. Yet large numbers can be misleading. A vast universe does not guarantee a repeated event. If the origin of life is extraordinarily unlikely, billions of planets might remain empty. If the process happens readily, when certain conditions gather, even a small region of the galaxy could contain many biospheres. The central uncertainty lies not in the number of worlds. It lies in the probability that chemistry becomes biology. Earth provides one confirmed example. Life exists here, which proves that the transition is physically possible. But a single example cannot reveal whether that transition is common or almost impossibly rare. Imagine discovering one tree on an unfamiliar island. Its presence proves that trees can grow there. It does not show whether the forest covers the entire island or whether this is the only tree for thousands of kilometers. Astronomy is beginning to map the island. More than 6,000 exoplanets have been confirmed, with new worlds continually added to scientific archives. Their sizes, temperatures, orbits, atmospheres, and host stars vary greatly. Surveys indicate that planets are ordinary companions to stars rather than unusual exceptions. But biology remains represented by only one known world. The universe offers an enormous number of opportunities. Science still does not know how often those opportunities become alive. The Drake equation was created to organize this uncertainty. In 1961, astronomer Frank Drake gathered several important questions into a single mathematical framework. The equation estimates how many technological civilizations might be detectable in the Milky Way at a given time. It begins with the rate at which stars form. It then considers the fraction of stars with planets, the number of potentially habitable worlds in each system, the fraction on which life begins, the fraction where intelligence evolves, the fraction that develops detectable technology, and the length of time such technology remains observable. The equation is sometimes mistaken for a machine that produces a reliable number. It is better understood as a map of ignorance. Each term represents a doorway between one stage and the next. Stars must form, planets must exist, suitable environments must appear, life must begin. Some life must become complex. Intelligence must develop technology. That technology must produce a signal during the same period that another civilization is able to detect it. A large value at one stage can be reduced by a very small value at the next. Billions of habitable planets would mean little if life begins on only one in a trillion. Common microbial life would not guarantee intelligent organisms. Many intelligent species might never build radio transmitters or explore space. The equation does not assume that every stage is likely. It simply separates the question into parts that can be studied. When Drake first proposed it, even the fraction of stars with planets was uncertain. Astronomers now know that planets are widespread, and exoplanet surveys have begun constraining how often small worlds occupy potentially temperate orbits. The later biological terms remain almost completely unknown. No measurement reveals how often life begins. No measurement shows how often simple cells evolve into complex organisms. No cosmic survey has yet established how long technological civilizations usually remain detectable. The equation's greatest value is therefore not its answer. It is the way it reveals precisely which answers are missing. Some terms in the equation have become more hopeful. Stars commonly possess planets. Small planets are abundant. Rocky worlds have been found in compact systems, broad systems, and orbits around several different types of stars. Planet formation also began early in cosmic history. One ancient planet identified through observations of the globular cluster Messier 4 is estimated to be around 13 billion years old. It formed long before the Sun and survived the changing lives and gravitational interactions of its stellar environment. This world is a gas giant, rather than a known habitat for life. Its importance lies in its age. It shows that planet formation was possible when the universe was still young. Worlds did not wait for the solar system to appear. Planetary systems had billions of years to form, change, and perhaps develop complex chemistry before Earth existed. The Sun is about 4.6 billion years old. Many stars in the Milky Way are older. If an Earth-like world formed several billion years before Earth, any life upon it would have received an enormous head start. This does not mean that its inhabitants would inevitably become advanced. Evolution has no fixed destination. A planet may remain inhabited only by microorganisms. Environmental changes may repeatedly interrupt complexity. Intelligence may emerge without developing technology. Still, time matters. On Earth, technological civilization appeared only after billions of years of biological evolution. Older stable worlds could, in principle, have passed through similar changes long before the first animals moved through Earth's oceans. When humanity looks across the galaxy, it may be looking toward worlds younger than Earth, worlds of similar age, and worlds unimaginably older. The inhabitants of another planet, should they exist, need not be at the same stage. Some biospheres may contain only their earliest cells. Others may have completed their histories before the solar system formed. The galaxy is not one clock. It is a field of clocks that began ticking at different moments. The age of the universe therefore creates both possibility and separation. There has been enough time for life to arise many times. There has also been enough time for entire civilizations to appear and disappear without ever overlapping. The first technological societies in the Milky Way may be separated from humanity, not only by thousands of light years, but by millions of years. Two civilizations can inhabit the same galaxy and never share the same cosmic evening. A radio signal remains detectable only while it travels through space and while someone is listening in the correct direction. A civilization could transmit for 10,000 years, which is a long span by human standards, yet still occupy only a tiny fraction of the galaxy's history. If another society sent signals 1 million years ago and then became silent, its transmissions may already have passed Earth. If a civilization will arise 1 million years from now, humanity's present searches cannot find it. This is why the lifetime term in the Drake equation is so important. Long-lived civilizations are more likely to overlap. Brief technological periods may pass like scattered flashes, rarely illuminating one another. Researchers Adam Frank and Woodruff Sullivan approached the equation from another direction. Rather than asking how many technological civilizations exist now, they asked whether humanity is likely to be the only technological species that has ever appeared in the observable universe. Their calculation showed that humanity would be cosmically unique only if the probability of a technological civilization developing on a potentially habitable world were extraordinarily small, roughly below 1 chance in 10 billion trillion across the observable universe. This is not evidence that another civilization exists today. It is a statistical threshold. The calculation depends on estimates of stars and potentially habitable planets, while leaving the unknown biological probability visible. It suggests that many past civilizations are mathematically possible, unless advanced life is exceedingly difficult to produce. The universe may have hosted many technological societies without any remaining close enough in time or space to communicate. A silent sky does not separate these possibilities. It cannot yet distinguish between a universe where intelligence is almost absent and one where intelligence appears occasionally but rarely overlaps. The silence creates a question often called the Fermi paradox. The idea begins with the enormous age and scale of the Milky Way. If technological civilizations are common, and if even a few develop interstellar travel, then some may have had enough time to spread throughout large portions of the galaxy. Even journeys far slower than light could cross interstellar distances over millions of years. That is a long period compared with human history, but short compared with the age of the galaxy. Why then is there no clear sign? No confirmed artificial signal has arrived. No verified alien spacecraft has been found. No unambiguous structure has appeared around another star. The apparent contradiction is summarized in one gentle question: where is everybody? The word paradox can make the problem sound stronger than it is. There is no proven contradiction because the starting assumptions remain uncertain. Science does not know whether life is common. It does not know whether intelligence commonly develops. It does not know whether civilizations expand between stars, remain close to home, become difficult to detect, or survive for long periods. Fermi's question is therefore not proof of absence. It is an invitation to examine the assumptions hidden inside expectations of abundance. One answer may be that simple life is common, while complex life is rare. Earth remained inhabited by microscopic organisms for most of its history. Bacteria and archaea can adapt to remarkable environments, reproduce quickly, and survive with relatively simple structures. Complex multicellular life requires additional conditions. Cells must cooperate, specialize, communicate, and regulate their growth. Organisms often require substantial energy. Stable environmental conditions may need to persist long enough for large bodies and nervous systems to evolve. Earth's oxygen-rich atmosphere also developed gradually. Photosynthetic organisms existed long before oxygen became abundant enough to support the energetic lives of large animals. Even after complex organisms appeared, only one known lineage produced a global technological civilization. This sequence may contain several difficult transitions. Perhaps life begins readily, but usually remains microbial. Such a galaxy could be biologically rich and technologically quiet. Oceans beneath ice might hold cells. Rocky planets could carry thin microbial films. Clouds, caves, sediments, and underground waters might contain living chemistry without producing radio transmitters or visible structures. The universe could be filled with life that never looks toward the stars. Another possibility is that intelligence appears in forms that do not develop recognizable technology. Intelligence on Earth is not confined to humans. Many animals solve problems, communicate, use tools, remember individuals, navigate over great distances, and maintain complex social relationships. Yet dolphins do not build radio telescopes. Octopuses do not construct satellites. Crows do not reshape planetary atmospheres through industry. Technology depends upon more than intelligence alone. It may require suitable bodies, accessible materials, social learning, environmental pressures, long lifespans, language, and the ability to control fire or another concentrated energy source. An ocean species might possess a rich inner life while finding metalworking difficult beneath water. A solitary intelligent organism might rarely exchange ideas across generations. A species living within a stable environment may never benefit from large-scale engineering. Human-style technology is one evolutionary path. It is not necessarily the inevitable expression of intelligence. Another world may support minds that compose, remember, communicate, and understand their environment without producing any signature that an interstellar telescope can recognize. The absence of detectable machines would not mean the absence of awareness. Some civilizations may also become quieter as they advance. Early technological societies might release broad radio emissions because their systems are inefficient and loosely directed. Later communication may move through fiber, narrow beams, low-power networks, or methods that allow very little energy to escape. Earth itself has changed in this way. Many strong television and radio broadcasts once leaked broadly into space. Modern communication increasingly uses satellites, cables, focused transmissions, and digital signals. A distant observer searching only for old-style leakage could find Earth less obvious than expected. Advanced societies may direct communication only towards selected receivers. A narrow beam carries energy efficiently, but illuminates little of the sky. Unless Earth happened to cross the beam, nothing would be detected. Technological activity could also move into environments difficult to observe. Machines might operate below planetary surfaces, within oceans, or in compact computational structures that release little waste heat. A civilization could value low energy use, environmental stability, or virtual experience rather than visible expansion. Human history offers no reliable guide to what a society millions of years older might choose. The assumption that all intelligence will spread widely and announce itself may reflect human imagination more than universal behavior. A civilization can exist without becoming loud. It can endure without covering the galaxy. The Fermi question sometimes assumes that expansion is inevitable. But crossing between stars remains difficult even for advanced technology. The nearest star system lies more than 4 light-years away. At the speeds of present spacecraft, such a journey would require thousands of years. Faster travel may be possible, but it demands energy, protection, navigation, and extraordinary reliability. A spacecraft moving through interstellar space encounters radiation and dust. Even tiny particles become dangerous at high velocity. Machines must survive for decades, centuries, or longer without repair from their place of origin. Living travelers would require food, water, shielding, and stable ecosystems. Generational voyages would need societies capable of remaining functional across many human lifetimes. Self-replicating machines could theoretically spread more easily. They might enter a planetary system, use local materials to construct copies, and send those copies onward. But this idea depends on technologies humanity has not developed, and on assumptions about why another civilization would choose to build them. Interstellar expansion is physically imaginable. It is not known to be socially or technologically inevitable. A galaxy can contain many civilizations that remain near their home stars. Distance would then preserve the quiet. Other explanations place the greatest difficulty earlier in the story. The origin of life itself may be the rare step. Earth's oceans and atmosphere formed early, and evidence suggests life appeared relatively soon in geological terms. This can be interpreted hopefully. Perhaps biology begins naturally when conditions become suitable. But Earth is the only planet from which observers are able to ask the question. Any intelligent observer must necessarily find itself on a world where life began early enough to allow intelligence to develop before the planet became uninhabitable. This creates a selection effect. The early appearance of terrestrial life may reveal that life begins easily, or it may simply reflect the fact that observers cannot arise on the countless worlds where life started too late or never started at all. One example cannot separate these possibilities. The same uncertainty applies to other major evolutionary transitions. Complex cells may be common, or they may have emerged through a rare event. Multicellular organisms may be a natural outcome or an unusual branch. Intelligence may evolve repeatedly under certain pressures, or Earth may represent a nearly unique pathway. Scientists sometimes describe a difficult, improbable transition as a filter. A great filter would be a stage that very few worlds successfully cross. The filter might lie behind humanity. Perhaps the origin of life, complex cells, multicellular organisms, or technological intelligence is extraordinarily rare. If so, Earth has already passed through an unusual sequence. The filter might instead lie ahead. Technological civilizations may commonly arise but rarely survive long enough to become visible across the galaxy. There is no evidence identifying one specific filter. The concept is a way of arranging unknowns, not a prediction that civilizations must destroy themselves. A civilization might become undetectable for many peaceful reasons. It could change its technology, lose interest in expansion, transform into a form that produces few recognizable signals, or simply remain local. The galaxy's quietness alone does not reveal where any barrier lies. Another answer may be that humanity has begun listening unusually early. The universe is about 13.8 billion years old, but many of its longest-lived stars have barely begun their existence. Red dwarf stars are smaller and cooler than the Sun. They are also the most abundant stellar type in the Milky Way. Some can continue shining for more than 100 billion years, far longer than the current age of the universe. Their planets may therefore possess astonishing spans of future time. Red dwarfs also create challenges. Young and active red dwarfs can release strong ultraviolet radiation, X-rays, and flares. Because their habitable zones lie close to the star, planets there receive intense exposure, atmospheres may erode, oceans may be lost, and surfaces may become difficult environments. Whether many rocky planets around these stars can retain atmospheres is an active subject of observation. If they can, the long future of red dwarfs may provide vast opportunities for biology. If they cannot, their abundance may contribute less to life than their numbers initially suggest. The TRAPPIST-1 system illustrates both sides of this possibility. Its 7 rocky planets orbit an ultra-cool red dwarf. The star is estimated to be older than the Sun, perhaps between about 5.4 and 9.8 billion years old. The planets have therefore experienced billions of years of stellar activity. Some may have lost large quantities of water. Others may have retained volatile materials or atmospheres. Current observations continue testing these possibilities. The star itself will shine far longer than the Sun. Small stars consume their fuel slowly, like candles that barely diminish across cosmic time. If some red dwarf planets remain habitable, then much of the universe's potential biological history may still lie in the future. Humanity could be early rather than late. The current universe may resemble the first quiet hour before a much longer age of living worlds. This possibility changes the meaning of silence once again. Perhaps the galaxy is not an ancient city that should already be crowded. Perhaps it is a young garden in which most seeds have not yet opened. The Sun belongs to a relatively short-lived stellar class compared with red dwarfs. Earth's technological civilization has appeared while the universe still contains abundant gas for future stars, and while the longest-lasting suns remain near the beginnings of their lives. There may have been civilizations before humanity. There may also be far more after it. No observation currently determines humanity's place in that sequence. Another factor is that searches do not cover the galaxy evenly. Radio telescopes observe selected targets, frequencies, and times. Optical searches monitor limited regions for short pulses. Infrared surveys examine large datasets but must distinguish technology from dust, stars, and galaxies. A civilization could be nearby and still escape detection if its signals are weak, intermittent, or directed elsewhere. Earth has not been broadcasting recognizable radio technology for very long. The expanding shell of humanity's earliest strong emissions has reached only a small region of the Milky Way. Most of the galaxy has not yet had enough time to receive evidence of modern human technology, much less respond. Even within that region, Earth's signals become faint. Any listener would need suitable instruments, attention directed toward the solar system, and an interest in signals resembling those humans happen to produce. The absence of an answer is therefore unsurprising. Most possible observers have not had the opportunity to hear the question. Scientists sometimes describe the search for extraterrestrial intelligence as examining a cosmic haystack. The haystack includes the whole sky, many frequencies, different types of signals, unknown transmission schedules, varying power levels, and civilizations at different distances. Human searches have examined only a tiny portion. Finding nothing within that portion does provide information. It can rule out certain powerful, continuous transmitters around particular stars at particular frequencies. but it cannot yet rule out technological life in general. Silence becomes meaningful only when the search is sufficiently broad and sensitive. Humanity has only begun to build that breadth. Statistics can guide the search, but they cannot replace evidence. The Drake equation may produce optimistic or pessimistic estimates depending on the values placed within it. Arguments based on the size and age of the universe can make other life appear likely. Yet likelihood is not detection. 1 billion possible inhabited planets do not equal one confirmed organism. A persuasive calculation cannot replace a cell, fossil, atmospheric biosignature, or artificial signal. The reverse is also true. The failure to detect life so far does not prove it absent. A small search cannot outweigh an enormous unexplored region. Science remains between these two temptations. It avoids declaring that life must exist simply because the universe is large. It also avoids declaring that Earth is unique simply because no second example has yet been found. The evidence currently supports a more careful statement. Planets are widespread. Potential habitats are numerous. Life's ingredients are common. Biology is possible because it exists on Earth. Everything beyond those statements remains open. This openness is not emptiness. It is a field of questions becoming measurable for the first time. The Drake equation once contained terms based almost entirely on imagination. Planet discoveries have now anchored some of them in observation. Atmosphere studies are beginning to examine habitability directly. Solar system missions can test oceans, sediments, and organic chemistry. The biological terms may eventually become data as well. One confirmed microbe beyond Earth would transform estimates of life's frequency. 2 independent biospheres would suggest that life can begin repeatedly. A technological signal would reveal that evolution has crossed from chemistry to intelligence somewhere else. Until then, probability remains a lantern rather than a destination. It illuminates the paths science might follow. It cannot show what waits at their ends. The scale of the universe offers no final proof that humanity is not alone. It offers something softer. It reveals that Earth is one world among an almost immeasurable population. It shows that planetary systems have existed for most of cosmic history. It provides room for life to begin early, late, nearby, far away, many times, or perhaps only once. The silence does not answer the question. The numbers do not answer it either. Together, they define the mystery. There are more possible homes than previous generations could have imagined, spread across more time than a human mind can easily hold. Some may be empty. Some may contain quiet oceans of cells. Some may have carried civilizations whose light passed Earth before anyone was watching. And somewhere within the enormous unfinished census, another world may still be waiting to become the second known place where the universe opened its eyes. Some of the most valuable moments in the search for alien life begin with evidence that later becomes something else. A spacecraft records an unexpected chemical reaction. A telescope detects an unusual signal. A meteorite contains structures resembling tiny fossils. For a brief time, each observation appears capable of changing humanity's understanding of life in the universe. Then the slower work begins. Other scientists repeat the analysis. New instruments examine the target. Alternative explanations are tested. Details that first seemed biological may emerge from geology, chemistry, dust, or human technology. The original mystery may become less extraordinary. But the investigation is not a failure. Every false alarm improves the next search. It reveals weaknesses in instruments, gaps in scientific models, and natural processes that can imitate life. It teaches researchers which evidence is persuasive and which evidence only appears persuasive at first. This is especially important in astrobiology. A discovery of extraterrestrial life would influence science, philosophy, religion, and humanity's view of itself. The evidence must therefore be strong enough to survive careful examination from many directions. An unexplained observation is not automatically an alien observation. The word unexplained describes the limits of present information. It does not identify the cause. A signal may remain unexplained because it was observed only once. A chemical may remain uncertain because the instrument operated near its sensitivity limit. A moving object may appear unusual because astronomers discovered it too late to collect complete measurements. Mystery creates a reason to investigate. It does not provide permission to choose the most exciting explanation. The history of the search is filled with discoveries that rested for a while between nature and biology. Each one added another step to the scientific ladder used to recognize life. Some steps held, others gently disappeared beneath closer observation. Together they taught science how difficult proof must be, and how carefully it must be built. The Viking landers carried the first experiments designed to search directly for life on another planet. Viking 1 reached the surface of Mars in July 1976. Viking 2 followed in September. Each lander carried cameras, weather instruments, chemical laboratories, and 3 biological experiments. The experiments examined Martian soil. They were designed to detect processes resembling metabolism, photosynthesis, or the exchange of gases associated with living microorganisms. One experiment became especially famous. The labeled release experiment placed a small sample of Martian soil inside a chamber. It added liquid nutrients containing radioactive carbon. If microorganisms consumed the nutrients, they might release radioactive gases that the instrument could detect. Soon after the nutrients were added, gas appeared. The response looked similar in some ways to what living microbes might produce. When another soil sample was heated strongly before the experiment, the response largely disappeared. Heat can destroy organisms. For a moment, the results seemed deeply promising. But the other Viking experiments did not provide clear supporting evidence. The lander's instruments also failed to detect the kinds of organic molecules expected within soil containing active organisms. Scientists began searching for chemical explanations. Martian soil is exposed to ultraviolet radiation and contains reactive substances. These compounds may respond to added water and nutrients without any biology being present. Decades later, NASA's Phoenix lander discovered perchlorate salts in Martian soil. When heated, perchlorates can destroy organic material and produce chemicals similar to some of those detected by Viking. This helped explain why Viking's organic analysis may have struggled and why its biology experiments behaved unexpectedly. Some researchers continue to argue that the labeled release result could have been biological. Most scientific assessments remain more cautious because the experiments did not provide a consistent collection of independent life signs. NASA describes the Viking results as providing no definitive evidence of life. Yet Viking transformed Mars exploration. It showed that life detection experiments must understand the surrounding chemistry before interpreting a reaction as biological. Water added to alien soil may awaken organisms, but it may also initiate unfamiliar reactions among salts, minerals, and atmospheric gases. The Viking landers did not settle the question. They placed the question directly into Martian soil and showed how carefully Mars could answer. 20 years later, a small rock from Mars created another moment of possibility. The meteorite is called Allen Hills 8401, often shortened to ALH 8401. It formed on ancient Mars more than 4 billion years ago. An impact later launched it into space. After traveling between the planets, it fell onto Antarctica, where researchers discovered it in 19. Scientists knew that the rock came from Mars because gases trapped inside it resembled the Martian atmosphere measured by the Viking landers. Within the meteorite were carbonate minerals and organic carbon compounds. Some microscopic structures appeared to resemble extremely small fossilized bacteria. Certain crystals of magnetite also looked similar to minerals that terrestrial microorganisms can produce. In 1996, a research team proposed that these features collectively represented possible evidence of ancient Martian life. The announcement captured worldwide attention. The idea was not based on one feature alone. It rested upon several lines of evidence appearing together: organic compounds, carbonate structures, magnetite crystals, and tiny shapes resembling organisms. But each line soon faced alternative explanations. Organic molecules can form without life. Carbonate globules can grow through geological processes. Magnetite crystals can emerge under high temperatures and pressures. The supposed microfossils were smaller than most known cellular organisms and could have been mineral structures rather than biological remains. There was also the possibility of contamination after the meteorite reached Earth. Further studies continued for years. Some researchers defended portions of the biological interpretation. Others showed that non-biological processes could reproduce important features. More recent analysis supports the conclusion that much of the organic carbon formed through interactions among Martian water, rock, volcanic processes, and impact chemistry, rather than organisms. The meteorite is no longer considered proof of Martian life, but it remains a precious record of ancient Mars. It confirms that water once moved through Martian rock. It preserves carbon chemistry from a period when the planet possessed environments more suitable for life than the surface has today. ALH84-1, also changed the culture of astrobiology. It showed that structures resembling fossils are not enough. Organic molecules are not enough. Minerals associated with biology are not enough, when geology can make similar forms. A convincing fossil must rest within a clear environment, possess structures biology explains better than chemistry, and survive analysis by independent methods. The meteorite did not reveal an ancient Martian cell. It revealed how closely lifeless minerals can resemble the memory of one. Venus produced another possible biosignature from within its clouds. The planet's surface is extremely hot. Its thick carbon dioxide atmosphere creates powerful pressure and heat, making the ground unsuitable for known terrestrial organisms. Higher in the atmosphere, conditions briefly become milder. At altitudes around 50 to 60 kilometers, temperatures and pressures can approach ranges familiar on Earth. The clouds remain strongly acidic and contain very little available water, creating serious difficulties for biology. Still, scientists have occasionally considered whether microorganisms could survive within cloud droplets. In 2020, a research team reported the possible detection of phosphine gas in Venus's atmosphere. Phosphine consists of phosphorus and hydrogen. On Earth, it is associated with certain microbes living in oxygen-poor environments, although humans also manufacture it industrially. Researchers had studied phosphine as a possible biosignature because it can be difficult to produce in large amounts on a rocky planet through familiar non-biological chemistry. The reported Venus signal appeared within radio observations at wavelengths where phosphine absorbs light. If the detection was correct, some continuing process would need to replenish the molecule because phosphine should not survive indefinitely in the Venusian atmosphere. The possibility of cloud life received renewed attention, but the signal was extremely delicate. Other researchers re-examined the data and questioned how the telescope observations had been processed. Sulfur dioxide, an ordinary component of Venus's atmosphere, can produce a nearby spectral feature. Later observations did not consistently confirm the original abundance. NASA's airborne ESOPHIA observatory searched for phosphine at other wavelengths and found no evidence of it, placing a strict upper limit on how much could be present. Some analyses of older spacecraft data have continued suggesting that small amounts may exist. Other studies remain unconvinced. Even a confirmed detection would not demonstrate biology. Unknown atmospheric chemistry, volcanic processes, lightning, or reactions involving minerals could potentially contribute. Scientists would need to understand where the gas was located, how its concentration changed, and whether any natural mechanism could maintain it. As of 2026, phosphine on Venus remains disputed rather than confirmed proof of life. NASA states that current findings provide no compelling evidence for organisms within the Venusian clouds. The debate has still achieved something important. It has inspired new laboratory experiments, improved models of Venusian chemistry, and increased interest in missions capable of sampling the atmosphere directly. The planet's clouds may ultimately reveal unfamiliar chemistry rather than biology. Either result would deepen understanding of how rocky planets evolve. The faint phosphine line did not become an announcement that life had been found. It became an invitation to return to Venus with better instruments. A distant star once appeared to offer possible evidence of enormous alien engineering. Its formal name is KIC 8462852. It is also known as Boyajian's star, or Tabby's star, after astronomer Tabitha Boyajian, who led early investigations of its unusual behavior. The Kepler Space Telescope watched the star for several years. Ordinary planets cause regular shallow decreases in starlight as they pass between their stars and Earth. The dips repeat according to the planet's orbit. Tabby's star behaved differently. Its brightness sometimes fell by several percent, and on rare occasions by more than 20%. The dips were irregular. They varied in depth, duration, and shape. A planet would need to be enormous to block so much light. Several natural explanations were proposed. Perhaps a family of comets crossed the star. Perhaps fragments from a planetary collision produced clouds of debris. Perhaps the star itself was changing in an unusual way. A more imaginative possibility also received attention. A sufficiently advanced civilization might construct a vast swarm of structures around its star to collect energy. Such a swarm could block changing portions of the starlight and create irregular dips. This idea was never the leading conclusion. It was a hypothesis considered because the star's behavior was initially difficult to explain. Astronomers searched for radio signals from the system and found no confirmed transmission. Infrared observations also failed to reveal the strong waste heat expected from an enormous energy-collecting structure. Most importantly, later observations measured the star's dimming at several wavelengths. The star became dimmer in blue light than in red and infrared light. Small dust particles naturally produce this color-dependent effect. They scatter shorter wavelengths more strongly. A large opaque structure would block different colors much more evenly. The results strongly favored dust. The exact arrangement and origin of the dust remain subjects of research, but the evidence does not support an alien megastructure. Tabby's star offers a gentle example of scientific imagination working correctly. Researchers were willing to consider technology because the observation was unusual. They then designed tests that could separate technology from nature. The star's colors provided the answer. What appeared from a distance like a possible construction around another sun became a shifting veil of fine material. The explanation became less technological, but no less beautiful. Dust smaller than grains of smoke was able to imitate one of humanity's grandest ideas about an advanced civilization. The first known object to enter the solar system from interstellar space inspired a similar debate. It was discovered in October 2017 by the Pan-STARRS telescope in Hawaii. Astronomers named it Oumuamua, a Hawaiian word associated with a messenger or scout arriving from afar. Its motion revealed that it was not gravitationally bound to the sun. It had entered from interstellar space, passed through the inner solar system, and was returning to the darkness between the stars. No object like it had ever been observed. Oumuamua changed brightness dramatically as it rotated, suggesting an unusual elongated or flattened form. It appeared reddish, perhaps because cosmic radiation had altered material on its surface during its long interstellar journey. As it moved away from the sun, its path showed a small additional acceleration. Comets commonly experience such motion. Sunlight warms their ice, releasing gas and dust in jets that act like tiny thrusters. But telescopes did not observe an obvious cometary tail around Oumuamua. The combination seemed strange. Some researchers suggested that the object might be extremely thin and pushed slightly by sunlight, much like a light sail. Because artificial light sails have been proposed as a method of interstellar travel, this led to speculation that Oumuamua could be technological. Most astronomers continued exploring natural explanations. The object may have released gas without producing easily visible dust. It may have contained forms of ice that behave differently from familiar comets. Its surface could have changed during millions of years in interstellar space. Several models have proposed hydrogen, nitrogen, carbon monoxide, or ordinary water-driven activity. Each model faces questions, and no single explanation has achieved complete agreement. No radio signal was detected from the object. No photograph resolved its surface. It was already small, faint, and moving away by the time its importance became clear. The available evidence does not establish that Oumuamua was artificial. NASA describes it as the first known interstellar object and discusses natural processes as the leading explanations for its unusual movement, while acknowledging that many physical details remain uncertain. Its importance lies in what it represents. Material from another planetary system crossed close enough for human telescopes to notice. It carried information about worlds around a different star, even though no spacecraft could reach it in time. Future surveys will probably find more interstellar visitors. Some will be discovered earlier. Astronomers may study their gases, shapes, rotation, and composition with much greater precision. A rapid response spacecraft might someday fly near one. Oumuamua was not proof of alien machinery. It was proof that fragments from distant planetary systems can wander through humanity's celestial neighborhood. The first visitor remained mysterious because science saw it only as it was leaving. Reports of unidentified objects within Earth's atmosphere are also sometimes presented as evidence of alien visitation. These reports are now often grouped under the term Unidentified Anomalous Phenomena, or UAP. The word unidentified has a precise meaning. It describes an observation that cannot be confidently classified using the available data. It does not mean that investigators have identified an extraterrestrial origin. Many reports are eventually connected to aircraft, balloons, satellites, drones, weather, optical effects, sensor behavior, or limited perspective. A light moving across a dark sky can be difficult to judge. Without a known distance, its true size and speed remain uncertain. A small nearby object may appear similar to a large distant one. Camera movement can make a stationary source seem to accelerate. Infrared instruments can produce shapes unlike ordinary visible images. Some reports remain unresolved because the recordings contain too little information. A brief video may lack accurate distance, wind conditions, radar measurements, or multiple viewing angles. Once the event has passed, those missing measurements cannot always be recovered. NASA assembled an independent study team to consider how UAP reports could be investigated scientifically. Its report emphasized better data, calibrated instruments, standardized observations, open analysis, and the use of multiple sensors. NASA has stated that it has found no credible evidence of extraterrestrial life and no evidence that UAP are extraterrestrial. This statement does not claim that every reported object has been identified. It separates two different ideas. An unresolved observation is a question. An extraterrestrial spacecraft is one possible answer among many, and it requires positive evidence. Such evidence might include clear measurements showing performance beyond natural or human technology, repeated observations by independent systems, physical material with a verified non-terrestrial origin, or communication revealing an intelligent source. A blurry shape or incomplete sensor record cannot carry that weight alone. The scientific study of UAP is still valuable. Unusual observations may reveal atmospheric effects, unknown equipment problems, safety concerns, new human technologies, or rare natural events. Better reporting systems can reduce confusion and protect both aviation and research. Careful investigation does not remove wonder, it gives wonder a method. If a truly extraordinary object ever enters Earth's atmosphere, the strongest response will not be immediate belief or immediate dismissal. It will be the collection of clear, complete, and independently testable evidence. False alarms appear in other parts of astronomy as well. Pulsars once seemed almost too regular to be natural. The WOW signals seemed to arrive from a fixed point in the sky but never returned. BLC-1 appeared to come from the direction of the nearest star before researchers connected it to human radio interference. K218b offered tentative hints of a molecule associated with terrestrial marine life, but independent analyses could not confirm the signal strongly enough. Each case followed a similar path. An unusual pattern appeared. Researchers measured it, questioned it, and searched for alternatives. Sometimes a natural explanation emerged. Sometimes human technology was responsible. Sometimes the information remained incomplete. The unresolved cases should not be pushed into either certainty. They are not confirmed aliens. They are also not meaningless. They reveal where instruments, theories, and observing strategies need to improve. A weak candidate may help researchers design a stronger experiment. A disputed atmospheric molecule may identify the exact wavelengths a future telescope should examine. A mysterious radio event may lead observatories to save more complete data and coordinate follow-up observations quickly. The search grows through correction. Science does not move only by confirming its first interpretations. It moves by allowing evidence to reshape them. This is why the strongest proof of extraterrestrial life will probably involve convergence. Several independent observations will point toward the same explanation. A future Mars sample may contain microscopic structures, complex organic molecules, isotope patterns, and minerals that all fit biological activity within the same ancient environment. A plume from an ocean moon may contain cell-like structures, repeating molecular patterns, and chemical imbalances that geology cannot reproduce. A distant planet may show water, moderate temperatures, oxygen, methane, seasonal cycles, and surface reflectance patterns that remain consistent across several telescopes. A technological signal may repeat from the same star, follow the expected motion of a distant planet, contain organized information, and be recorded by observatories on different continents. Each line will support the others. Natural explanations will be tested deliberately rather than mentioned only after the discovery is announced. Independent teams will reprocess the data. New observations will attempt to reproduce the result. Confidence may rise gradually. At first, researchers may describe an interesting feature, then a candidate biosignature, then strong evidence difficult to explain without biology. Only after the alternatives have been reduced sufficiently will the word discovery become appropriate. This careful process may feel slower than imagination, but it protects the meaning of the result. The universe contains unfamiliar chemistry, unexpected objects, and physical events not yet fully understood. Any of these can imitate the signs researchers hope to find. The first convincing proof must therefore show more than strangeness. It must show a pattern that life explains better than every tested non-living process. Until then, the almost discoveries remain valuable landmarks. Viking teaches that Martian soil can perform surprising chemistry. ALH 8401 teaches that minerals can resemble fossils. Venus teaches that weak spectral lines demand independent confirmation. Tabby's star teaches that dust can imitate enormous engineering. Oumuamua teaches that the first example of a new natural population may appear unlike anything seen before. UAP research teaches that incomplete information should remain incomplete rather than being filled with certainty. None of these mysteries proves that humanity is alone. None proves that humanity has company. They stand between those conclusions, quietly refining the question. The search has not failed because its most famous candidates became uncertain or natural. It has learned, and with each lesson, science becomes a little more prepared for the observation that does not disappear under closer examination. Someday, another signal may return. Another atmosphere may reveal the same molecule through several instruments. Another sample may preserve structures that chemistry alone cannot explain. The evidence will be questioned, it will be tested, and perhaps for the first time, every ordinary explanation will slowly fall away, while the possibility of life remains. The first confirmed discovery of extraterrestrial life may begin with something remarkably small. It may be a pattern inside an ancient Martian rock. It may be a molecule frozen within a grain of ice from another moon. It may be a narrow group of wavelengths missing from the light of a distant planet. The evidence may first appear as a line on a graph. Only later will its meaning become clear. Science is now building several different paths toward that discovery. Some missions travel directly to nearby worlds. Others study planets across light years of space. Laboratories on Earth prepare to examine samples with instruments too large and sensitive to place aboard a spacecraft. No single path is guaranteed to succeed. Together, they create a search much broader than anything attempted before. The strongest proof will probably emerge through several connected observations. A promising molecule must appear repeatedly. Its environment must be suitable for biology. Geological and chemical alternatives must be tested. Independent instruments must reach compatible conclusions. Discovery may therefore unfold in stages. The first observation raises a possibility. The second strengthens it. The third removes an ordinary explanation. Gradually, an unfamiliar pattern becomes difficult to understand without life. This process may take months or years. It may involve many observatories, spacecraft, laboratories, and research teams. The first evidence may arrive quietly. Its confirmation will be built slowly. On Mars, Perseverance is preserving pieces of an ancient environment for future laboratories. The rover explores Jezero Crater, where a river once entered a lake and deposited sediment in a broad delta. Water carried minerals and fine material into the basin billions of years ago. Lake sediments are valuable because they can preserve chemical and structural traces. On Earth, mud and clay sometimes protect organic molecules from heat, radiation, and chemical destruction. Fine sediments can also preserve microscopic textures left by organisms. Perseverance drills cylindrical cores from selected rocks. Each core is placed inside a clean titanium tube. The tube is photographed, sealed, and stored. Some remain aboard the rover, while a backup collection has been placed carefully on the Martian surface. The samples include igneous rocks, sedimentary material, dust, and atmospheric gas. Special witness tubes help scientists understand whether any contamination came from the spacecraft itself. By July 24, 2025, NASA had documented 33 sample tubes used by Perseverance. Their contents preserve a carefully selected geological history that may someday be examined on Earth. A laboratory on Earth can do much more than a rover laboratory. A sample can be divided among many research groups. Scientists can use large microscopes, particle accelerators, mass spectrometers, and instruments not yet invented when the rock was collected. They can repeat measurements. They can examine individual mineral grains, map organic compounds, and measure isotope ratios with extraordinary precision. One instrument may identify a structure, another can test its age, a third can reveal whether its chemistry fits biology or geology more naturally. No fixed date currently guarantees that the Perseverance samples will return to Earth. The architecture for retrieving them has continued to evolve. The tubes therefore wait as preserved opportunities rather than completed discoveries. Their value remains. A sealed piece of Mars can be studied by generations of scientists. Its meaning does not depend on one spacecraft or one moment. If a sample contains evidence of ancient life, the proof may emerge from relationships among several features. Organic molecules could appear within a sedimentary layer known to have formed in water. Their carbon might show unusual isotope ratios. Minerals could display patterns associated with microbial activity. Microscopic structures might repeat in organized forms rather than appearing as random cracks. Each feature alone could be uncertain. Together they could form a biological history. The rock would not simply contain carbon. It would preserve a sequence of events that chemistry without life could not easily reproduce. Even a negative result would teach something important. If the most promising ancient Martian environments contain no convincing biological trace, the origin of life may require more than water, carbon, and time. Mars is preparing a test of whether a once habitable world was ever truly inhabited. Farther away, Europa Clipper is already traveling toward Jupiter. The spacecraft launched on October 14, 2024. It is scheduled to enter the Jupiter system in April 2030 and conduct 49 close flybys of Europa. Its goal is not to detect organisms directly. It is designed to determine whether Europa possesses conditions capable of supporting life. That distinction allows the mission to ask several foundational questions. How thick is the icy shell? How deep is the ocean? Does liquid water rise close to the surface? Which salts and organic compounds exist within the ice? How much energy is available? Does the rocky interior interact with the water above it? Europa Clipper carries cameras, spectrometers, radar, magnetic instruments, thermal sensors, and equipment for analyzing particles and gases around the Moon. Ice-penetrating radar will send radio energy toward the surface. Some of that energy may reflect from layers, fractures, and possible reservoirs of liquid water below. The spacecraft will measure Europa's magnetic response to Jupiter. Because salty water conducts electricity, the changing magnetic field can reveal properties of the hidden ocean. Spectrometers will examine the surface composition. They may distinguish salts, water ice, organic compounds, and material altered by radiation. Thermal instruments will search for warmer areas where recent activity may be occurring. The spacecraft will also examine Europa's extremely thin atmosphere and the particles surrounding the Moon. If water vapor or small grains escape from the surface, they may carry information from shallower reservoirs or perhaps the ocean itself. Europa Clipper will not orbit Europa directly. Jupiter's radiation environment is intense. Repeated close flybys allow the spacecraft to collect detailed observations while spending much of its time farther from the strongest radiation. Each encounter will cross a different region. Over time, the flybys will assemble a global understanding from many narrow passages. A promising result might show a relatively thin region of ice, active exchange between the ocean and surface, useful chemical compounds, and energy-producing interactions between water and rock. None would prove that the ocean contains life. Together, they would reveal whether Europa provides biology with a stable place to begin and continue. The mission could also identify the best locations for a future lander. A later spacecraft might touch Europa's surface, drill into young ice, or analyze freshly deposited material near an active fracture. The journey toward direct detection often begins by finding the safest and most informative place to look. Europa Clipper is mapping that path before any instrument attempts to search for cells. Saturn's moon Titan will receive an explorer, unlike any sent to the outer solar system. Dragonfly is a rotorcraft lander with 8 rotors. It is designed to fly through Titan's dense atmosphere and move between many locations rather than remaining at one landing site. NASA currently lists its launch as no earlier than July 2028, with arrival at Titan in late 2034. Flight on Titan is unusually practical. The atmosphere is much denser than Earth's, while Titan's gravity is much weaker. A large rotorcraft can lift itself relatively efficiently and travel across dunes, plains, and impact structures. Dragonfly will not search only for present organisms. Its central goal is to investigate habitability and prebiotic chemistry, the chemical processes that may occur before life begins. Titan contains abundant organic material. Sunlight and energetic particles transform methane and nitrogen high in the atmosphere. Complex carbon-bearing compounds form within the orange haze and settle slowly toward the surface. Across billions of years, this process has covered Titan with a natural collection of organic chemistry. Most of the surface remains extremely cold. Water behaves like rock, while methane and ethane move through clouds, rain, rivers, lakes, and seas. Yet large impacts can melt water ice temporarily. In those places, liquid water may mix with organic compounds before freezing again. Dragonfly plans to explore the organic dunes near its landing area, and later travel toward the Selk impact crater. Within such an impact environment, liquid water and complex carbon chemistry may once have occupied the same location. The rotorcraft will analyze surface materials, study atmospheric conditions, monitor seismic activity, and examine the chemical structures of Titan's organic compounds. It may discover amino acids or other molecules relevant to life. Such molecules would still not prove biology. They would show how far natural chemistry can progress within a world very different from Earth. Titan may preserve stages of chemical evolution that Earth no longer contains. On the young Earth, oceans, plate tectonics, weather, and living organisms repeatedly altered the surface. Earlier molecules were consumed, buried, or transformed. Titan's deep cold may preserve chemistry much longer. Its landscape can act like a planetary archive. Dragonfly may reveal whether complex organic material naturally organizes into increasingly elaborate forms. It may show whether temporary water environments create molecules resembling those used by terrestrial cells. The mission will explore the boundary before life. Understanding that boundary is essential, because the discovery of ingredients alone can otherwise be mistaken for the discovery of organisms. Dragonfly may not find life. It may teach science exactly how close a lifeless world can come. Other missions will enlarge the collection of potentially habitable planets. ESA's Plato Observatory is designed to study terrestrial exoplanets, including worlds within the habitable zones of sun-like stars. Its 26 cameras will monitor more than 200,000 stars, searching for the small repeated dimming caused by planetary transits. ESA has stated that Plato is expected to be ready for launch around the end of 2020. Plato will do more than count planets. It will study vibrations within their host stars. Stars gently expand and contract. These oscillations create small changes in brightness. By measuring them, astronomers can estimate a star's size, mass, internal structure, and age. Knowing the star accurately improves knowledge of the planet. The depth of a transit reveals a planet's size relative to its star. If the stellar radius is uncertain, the planetary radius is uncertain as well. Age is equally important. A young planet may still be experiencing intense impacts, atmospheric loss, and volcanic activity. An older planet may have enjoyed billions of years of stable conditions. Plato aims to discover systems containing rocky planets, whose stars resemble the Sun, and whose years are long enough to place them in potentially temperate regions. These worlds are difficult to detect. An Earth-like planet transits a Sun-like star only once each year. Astronomers generally need several transits to confirm that the dimming repeats. The planet also blocks only a tiny fraction of the star's light. Finding it requires patient observation. Plato's discoveries will become targets for other telescopes. Once a promising world's size, orbit, star, and age are known, spectroscopic instruments can begin investigating its atmosphere. The telescope that finds a planet may not be the telescope that finds life. Discovery is often a relay. One mission identifies the world, another measures its mass, another separates its light, another reads its atmosphere. By the time a possible biosignature appears, many instruments may already have contributed to understanding the planet. The Nancy Grace Roman Space Telescope will help develop one of the most difficult abilities required for this search. A planet is faint beside its star. The challenge resembles trying to see a small firefly beside a powerful searchlight from thousands of kilometers away. Even when a planet and star appear separated on the sky, scattered starlight can overwhelm the planet's weak reflection. A coronagraph suppresses that starlight. It uses carefully shaped masks, mirrors, and wavefront controls to create an extremely dark region within the telescope's image. A planet that was hidden within the star's glare can then begin to emerge. Roman will carry a coronagraph instrument as a technology demonstration. It is intended to show advanced methods for directly imaging exoplanets by blocking their host star's light. Roman's coronagraph is not expected to photograph an exact twin of Earth. Its likely targets include larger planets and disks of dust surrounding nearby stars. But the technology is a bridge. It will test mirrors that change shape by extremely small amounts. These mirrors correct distortions within the incoming light and maintain the dark region needed for direct imaging. It will test how accurately a space telescope can remain aligned. It will study how starlight behaves inside a real observatory, rather than only inside a laboratory. A future telescope searching for Earth-like planets will require even greater contrast. Earth reflects only a tiny portion of the Sun's light. From a distant system, the planet would almost disappear within the surrounding glare. The path from Roman to a future living world image is therefore similar to learning to hear a whisper beside a waterfall. The waterfall cannot be removed. The instrument must create a small region of extraordinary quiet. Ground-based observatories will contribute through immense collecting areas and extremely detailed spectra. The European Southern Observatory's extremely large telescope is being built in Chile's Atacama Desert. Its primary mirror will span about 39 meters, formed from hundreds of individual segments. ESO currently plans the telescope's first light for March 20. Habitable exoplanets are among the areas expected to benefit from its sensitivity and resolution. A telescope this large collects more light from faint objects. It can also separate finer details. Adaptive optics will measure distortions introduced by Earth's atmosphere and reshape mirrors to correct them many times each second. Without this correction, moving air blurs the image. The ELT may analyze atmospheres of smaller planets than present ground-based telescopes can study effectively. It could search for molecules within planets orbiting nearby red dwarfs. It may measure winds, temperatures, and perhaps magnetic effects in distant atmospheres. Ground telescopes face limitations. Earth's own atmosphere absorbs some wavelengths. It contains water, oxygen, methane, and carbon dioxide, the same gases researchers seek on exoplanets. Scientists must separate the local atmosphere from the distant one. Space telescopes avoid much of this interference, while ground telescopes can be built with much larger mirrors. The two approaches complement one another. A possible biosignature seen from space may be tested from the ground at another wavelength. An atmosphere measured during a transit may later be observed through reflected light. Different instruments contain different sources of error. Agreement among them is therefore far more persuasive than one result alone. Beyond these observatories lies a mission designed specifically around the search for living worlds. NASA's Habitable Worlds Observatory is still a developing mission concept rather than a launched spacecraft. Its central objective is to directly image approximately 25 potentially habitable planets around other stars and use spectroscopy to search their atmospheres for biosignatures. The observatory would block the overwhelming light of nearby stars and collect the faint reflected light of planets around them. Within that light may be evidence of clouds, oceans, surface minerals, atmospheric pressure, and temperature. Spectroscopy could search for water vapor. It could examine oxygen, ozone, methane, carbon dioxide, and other gases. It could test whether combinations of molecules remain far from chemical equilibrium. Direct imaging offers an advantage over transits. A planet does not need to pass directly in front of its star from Earth's perspective. The telescope can observe reflected light from worlds in many orbital orientations. Repeated images can trace the orbit. The planet may brighten and fade through phases, much as the Moon does. Changes in color could suggest clouds, continents, oceans, or seasonal activity. The greatest challenge is contrast. A Sun-like star can be billions of times brighter than the visible light reflected from an Earth-like planet. The telescope's optics must remain extraordinarily stable. Tiny vibrations or temperature changes can move starlight into the region where the planet is being measured. Mirrors must be controlled with precision smaller than the width of an atom. The engineering sounds almost impossibly delicate, yet similar steps once separated earlier dreams from present astronomy. Detecting an exoplanet was once uncertain. Now thousands are known. Measuring atmospheric molecules across hundreds of light years once appeared unreachable. Webb now performs such measurements. HWO represents the next gradual step, moving from worlds that are easiest to observe toward worlds that most closely resemble Earth. NASA cautions that one possible biosignature would not by itself constitute a discovery of life. Convincing evidence would probably require multiple unambiguous biosignatures, atmospheric modeling, and observations from several missions over years. This may be how the first distant living planet is recognized. The observatory photographs a pale point beside a star. Its spectrum contains water. Later observations reveal oxygen and methane. Climate models suggest moderate surface conditions. The gases persist despite chemical reactions that should remove them. Seasonal changes repeat across the planet's orbit. Other telescopes confirm the measurements. Models of volcanoes, sunlight, oceans, and rock fail to reproduce the complete pattern. No city becomes visible. No creature is photographed. Yet the planet's atmosphere, behaves as though an entire biosphere is continuously reshaping it. The proof would exist not as an image of an organism, but as the combined breath of a world. Technology searches will expand beside the search for biology. Radio observatories continue collecting immense datasets from nearby stars, the center of the Milky Way, and galaxies beyond. The next technological signal might not be identified while the observation is being made. It may be discovered years later by a better algorithm. Radio data contain interference from satellites, aircraft, electronics, and ground transmitters. They also contain natural pulses from stars, gas clouds, and compact objects. Computers must examine countless patterns. Machine learning systems can be trained to recognize ordinary interference and search for signals that behave differently. They can identify drifting lines, short pulses, repeating groups, and structures older software was not designed to notice. Artificial intelligence does not remove the need for confirmation. An algorithm may find a candidate. Telescopes must still return to the same star. Independent observatories must attempt to observe it. Engineers must search for hidden sources of interference. Astronomers must determine whether nature can produce the pattern. But computation can enlarge the region being searched. It can revisit archives. A signal recorded before its significance was understood may still be waiting on a storage system somewhere on Earth. Optical instruments will monitor the sky for laser flashes. Infrared surveys will search for unusual waste heat. Atmospheric telescopes may look for industrial molecules. Planetary imaging may reveal artificial night-side illumination far beyond anything produced by natural processes. Most candidates will have natural explanations. That is expected. A broad search encounters more dust, stars, storms, magnetic events, and unfamiliar chemistry before it encounters technology. Every natural explanation becomes part of the filter used for the next observation. Proof of intelligence would require behavior difficult for nature to imitate. A radio signal might contain mathematical structure or information. It might repeat from a planet's location and follow the planet's orbit. A laser could pulse in a deliberate sequence. An atmospheric chemical might be present at concentrations difficult to produce through geology, while appearing alongside other signs of industrial activity. The source would need to remain visible after the telescope moved, the software changed, and independent teams examined the data. The first candidate might create excitement. The second observation would create responsibility. Scientists would need to protect the evidence from both exaggeration and premature dismissal. A genuine discovery will also require careful communication. Research normally advances through specialized papers, conferences, and gradual debate. Evidence for extraterrestrial life would attract immediate worldwide attention. Early results may be misunderstood. A candidate biosignature can easily become alien life discovered before alternative explanations have been studied. An unexplained signal can become alien message even when it has not repeated. Scientists will need clear language. Possible evidence is not strong evidence. Strong evidence is not confirmation. Confirmation requires independent support and the removal of reasonable alternatives. This careful vocabulary may appear restrained, but it preserves trust. The discovery belongs not only to the team operating the first instrument, it must become accessible to the wider scientific community. Data should be shared where possible. Methods should be described. Other researchers should be able to repeat the analysis and disagree openly. The conclusion becomes stronger when it survives people actively trying to show that it is wrong. Planetary protection will remain equally important. A possible Martian organism must be separated from contamination carried from Earth. Organic compounds detected on Europa or Titan must be traced through every material used to build and clean the spacecraft. Return samples will require controlled facilities. Scientists must document how the containers were sealed, transported, opened, and divided. Blank samples and witness materials will reveal whether terrestrial molecules entered during the process. The proof of alien life must include proof of alien origin. A terrestrial microbe hidden within a spacecraft can imitate one of the greatest discoveries imaginable. Careful engineering prevents that confusion long before a sample reaches a microscope. There may also be no single first discovery. Several weak clues could appear around the same period. A Martian sample may reveal unusual organic structures. An exoplanet atmosphere may contain a difficult combination of gases. A radio observatory may record a repeating signal. Each would develop independently. Together they could transform the search from one unanswered question into several active investigations. Or the first proof may be completely unexpected. Life elsewhere may use chemical structures unfamiliar on Earth. A biosphere may inhabit clouds rather than surfaces. An artificial signal may operate outside the frequencies now considered practical. Science designs missions using the best present understanding. The universe is not required to follow those designs. This is why broad instruments are valuable. A camera built to map ice may notice a plume. A spectrometer built to measure minerals may find an organic pattern. A telescope studying stellar activity may detect a planet. A radio survey, examining natural bursts, may uncover a narrow artificial signal. Many discoveries begin as unexpected information inside an experiment built for something nearby. The future search will therefore combine focused questions with open attention. Europa Clipper asks whether an ocean moon is habitable. Dragonfly asks how far complex chemistry progresses on Titan. Plato asks where older Earth-sized planets orbit sun-like stars. Roman tests how to separate planets from starlight. The ELT gathers finer spectra from faint worlds. The Habitable Worlds Observatory is being shaped around the direct search for nearby living planets. Perseverance preserves material that Earth laboratories may someday examine atom by atom. Each mission approaches life from a different direction. Water, chemistry, atmospheres, energy, geological history, technology. No mission promises an answer, but they make the absence of an answer increasingly measurable. A century ago, scientists did not know whether planets surrounded other stars. A few decades ago, the atmospheres of those planets were beyond observation. Today, spacecraft cross the plumes of ocean moons, rovers seal samples on Mars, and telescopes identify carbon-bearing molecules in skies more than 100 light-years away. The search is no longer only philosophical. It has become experimental. The coming instruments will not merely ask whether life might exist. They will examine specific oceans, specific rocks, specific atmospheres, and specific stars. Some results will close possibilities, others will create new ones, and one observation may remain after every test. It may begin as a faint line, a microscopic structure, or a repeated pulse. Other instruments will look, other teams will calculate. Months will pass. The ordinary explanations will be examined one by one. Then perhaps, the evidence will reach a quiet threshold. For the first time, the simplest remaining explanation will be that somewhere beyond Earth, matter has become alive. The evidence gathered across the search forms a picture without yet forming a conclusion. Planets are common. Water exists throughout planetary systems. Organic molecules form in clouds, meteorites, asteroids, moons, and ancient rocks. Several nearby worlds contain environments where known organisms might survive. Distant atmospheres can now be measured. Radio telescopes can listen to millions of narrow channels. Spacecraft can touch material released from hidden oceans. Rovers can examine lake beds that formed billions of years ago. Every discovery expands the number of possible homes for life. But a possible home is not proof of an inhabitant. NASA's current scientific position remains clear. No life beyond Earth has been confirmed, and no credible evidence shows that extraterrestrial organisms have visited this planet. That sentence may sound like an ending. It is actually the beginning of the most careful part of the search. Science now knows where many of the clues might appear. It knows which natural processes can imitate them. It knows that one unusual molecule, one radio pulse, or one microscopic shape cannot carry the entire conclusion. Real proof will require a pattern. The evidence must rise beyond habitability and beyond intriguing chemistry. It must show that a living process explains the observation better than every reasonable non-living alternative. This is why researchers use frameworks such as the ladder of life detection. A discovery begins near the lowest steps with an environment capable of supporting biology. Higher steps include organic material, unusual chemical organization, possible metabolism, biological structures, and repeated measurements supported by environmental context. Each step must rest upon the ones below it. The ladder does not provide one perfect formula for recognizing life. It offers a way to prevent excitement from moving faster than evidence. The first convincing proof may come from a nearby world. Mars is one possibility. Ancient sediment could contain organic compounds arranged in patterns that geology struggles to create. Minerals might preserve microscopic textures associated with cells. Isotope ratios could show that certain atoms were repeatedly selected by metabolism. None of these observations would be interpreted alone. The structures would need to appear within the correct geological layer. The molecules would need to be indigenous to Mars rather than contamination from Earth. Their age would need to match the ancient environment around them. Different laboratories would examine the same material. One might map the minerals, another might study carbon, another might search for repeating molecular structures, another might recreate possible non-biological processes and test whether they produce the same result. The evidence would become convincing only when these separate paths arrived at one shared history. Long ago, liquid water covered the sediment. Chemistry gathered there. And within that chemistry, something organized itself, used energy, reproduced, and left traces inside the rock. Such a discovery would reveal ancient life rather than a living organism. It would still transform the known universe. The stones of two neighboring planets would then contain biological histories. Earth would no longer be the only world where matter became alive. Europa or Enceladus may provide a different kind of proof. Their oceans may still exist today. A spacecraft could pass through a plume and collect frozen grains released from below the ice. Most grains would contain ordinary water, salts, and simple compounds. One grain might contain something more organized. It could hold complex molecules appearing in repeating groups. It could contain structures resembling membranes. Its chemistry might favor one molecular orientation in a way ordinary reactions do not. Several grains could show the same pattern. The molecules might appear alongside chemical imbalances, indicating that something continuously uses energy within the ocean. A single complex molecule would remain uncertain. A family of related molecules could be stronger. A repeating system of information-bearing chemistry, enclosed structures, and energy use would become difficult to explain without biology. The spacecraft would need to prove that the material came from the moon. It would need to document every substance used during construction. Control samples would reveal whether anything entered from Earth. Independent missions might later return. They would fly through the plume at different times and collect the same structures using different instruments. The evidence would gather slowly, grain by grain. An ocean hidden beneath ice would become the second known biosphere. The organisms might be simple. They might consist only of cells floating near chemical gradients or resting inside mineral pores. They would not need eyes, voices, or recognizable shapes. Their existence alone would answer the central question. Biology would have begun beyond Earth. A distant atmosphere may reveal life without providing a physical sample. The planet could appear as one faint point beside its star. No continent would be clearly visible. No organism could be photographed. Yet the planet's atmosphere might carry the combined activity of an entire biosphere. Water vapor could show that moisture moves through the atmosphere. Carbon dioxide could reveal part of the climate system. Oxygen might appear in quantities difficult to maintain through sunlight and geology alone. Methane could exist beside that oxygen despite reacting with it. The two gases would continuously remove one another. Their continued presence would suggest that active processes keep replacing them. Scientists would test volcanoes, impacts, oceans, radiation, and atmospheric escape. They would model the host star. They would examine whether ultraviolet light could create the observed oxygen. They would search for carbon monoxide or other molecules that might reveal a non-biological process. The planet would be observed through several seasons. Its gases might rise and fall in a repeated rhythm. Surface colors could change as different regions rotated into view. No single feature would prove life, but water, climate, reactive gases, seasonal cycles, and unusual surface reflection could converge. Several telescopes might measure the same world at different wavelengths. Each would provide another part of the atmosphere's story. Eventually, the biological explanation might require fewer assumptions than every alternative. Humanity would not see the inhabitants. It would see their collective influence. The first distant biosphere could be recognized as a planet whose atmosphere never becomes chemically still. Technological intelligence could provide an even clearer signal. A radio telescope might detect a narrow transmission from the direction of another planetary system. The signal would drift in frequency as the source rotated and orbited its star. The telescope would turn away. The signal would disappear. It would return when the telescope pointed back. Another observatory, separated by thousands of kilometers, would detect the same transmission. Local interference would no longer explain it. The signal might repeat. Its pulses could form a mathematical sequence. It might contain structured information rather than random noise. The source could move consistently with a known planet. Natural objects create remarkable patterns. Pulsars produce regular pulses. Magnetars release powerful bursts. Atmospheric and electronic effects can imitate artificial signals. But nature is not expected to transmit a long, organized sequence carrying compressed information. A verified message would therefore move quickly toward the highest levels of evidence. It would not require a photograph of the sender. The arrangement of energy would reveal intention. NASA includes such artificial signals, engineered atmospheric chemicals, and large-scale technological structures within the scientific search for technosignatures. No confirmed technosignature has yet been detected. The first message may not be intended for Earth. It could be communication between two planets in another system. A narrow beam might pass briefly across the solar system. It might be radar used to map asteroids. It might be an automatic beacon created long before its builders disappeared. The information could be impossible to translate. Humanity might detect organization without understanding meaning. Even that would be enough. A repeating artificial pattern from beyond the solar system would show that another intelligence learned to control energy and place information inside light. The universe would contain at least two technological histories. Communication would present a separate challenge. A signal from 100 light-years away began its journey a century earlier. A reply would require another century to arrive. Conversation could unfold across generations. Questions sent by one group of researchers might be answered for descendants they would never meet. Yet the first exchange need not resemble an ordinary conversation. Simply knowing that another mind exists would connect two worlds across the distance. A sequence of numbers could become a quiet bridge between separate branches of cosmic history. The nature of alien life may make the discovery difficult to recognize. Every current search begins with terrestrial experience. Earth life uses liquid water. It relies upon carbon chemistry. It stores genetic information within DNA and RNA. Its cells use membranes, proteins, and familiar elements. These features guide exploration because they provide the only confirmed example. But another origin may produce differences. Alien organisms might use unfamiliar molecules to carry information. Their membranes might remain stable under different temperatures or solvents. Their metabolism could depend on chemical reactions that play only minor roles on Earth. Some differences would still be limited by physics. A living system needs an energy source. It needs a way to maintain organization. It needs some process that preserves information while allowing variation and evolution. The exact materials may differ while the deeper requirements remain. This creates one of the search's greatest challenges. An instrument designed only to find terrestrial molecules may overlook biology organized in another way. Researchers therefore search for patterns as well as ingredients. Living systems often select certain molecules, concentrate particular elements, create repeating structures, and push their environments away from equilibrium. Alien biology may be chemically unfamiliar, while still leaving these broader signs. The strongest discovery would be life with an independent origin. A Martian organism might resemble Earth life, because rocks have traveled between the two planets. Material ejected by impacts can cross interplanetary space. If organisms survived such a journey, Earth and Mars could share one ancient biological family. That would still be extraordinary. It would show that life can travel between worlds. But it would not reveal whether life began independently twice. An organism from Europa or Enceladus would be harder to connect to Earth through ordinary rock exchange. If its chemistry differed fundamentally from terrestrial biology, the case for a separate origin would become strong. Perhaps it would use different molecules for genetic information. Perhaps it would favor the opposite molecular handedness. Perhaps its cellular machinery would have no relationship to proteins used on Earth. Two independent origins would provide the first real measurement of life's tendency to begin. The solar system would contain several worlds with suitable environments, and at least two would have crossed the boundary into biology. Life would no longer appear as one isolated chemical accident. It would look like a process that nature can repeat. That conclusion would extend far beyond the solar system. The galaxy contains more than 6,200 confirmed exoplanets already, while the true planetary population is vastly larger. If life began independently twice within one planetary system, then worlds orbiting other stars would become even more compelling. Every ocean moon would matter more. Every wet rocky planet would become a stronger possibility. The discovery of simple organisms nearby could therefore transform expectations about distant intelligence, even without proving that intelligence is common. Evolution would still contain many unknown steps. Microbial life might appear readily, while complex organisms remain unusual. Intelligence might depend on a rare sequence of environmental and evolutionary events, but the first and most fundamental barrier would have been crossed more than once. The universe would know how to begin living. Proof of life would not answer every question. It would create a new science. Researchers would ask how the organism gathers energy. They would study its molecular structures and reconstruct its evolutionary history. They would examine whether it changes its environment. They would ask whether it possesses ancestors, competitors, predators, partnerships, or ecosystems. A simple cell could contain chemistry unknown on Earth. Its proteins, or their alien equivalents, might inspire new materials and medicines. Its genetic system could reveal alternative ways of storing information. Its existence would reshape ideas about evolution. Features once thought essential might prove local to Earth. Other patterns might appear universal, repeated whenever matter organizes into living systems. The discovery would also change the way humanity understands its own biology. Earth life would become one example rather than the definition of life itself. The tree of terrestrial organisms would remain vast and beautiful, but it would stand beside another tree, rooted in a separate world. A technological civilization would raise still more questions. How long has it existed? Does it understand its own biological origin? Has it found other civilizations? Does it explore physically, communicate remotely, or remain near its star? Its message might contain science. It might contain art. It might contain only a simple announcement that something capable of building a transmitter once existed there. Humanity could discover a civilization that is still active. It could also discover an echo. Because light carries the past, telescopes may observe a society that changed or disappeared before its signal reached Earth. The message would remain meaningful. It would show that intelligence is not an event limited to one planet. The universe would have produced minds in separate places. There is also a quieter possibility. The search may continue for generations without reaching proof. Mars samples may contain ambiguous chemistry. Europa may possess an ocean without recognizable organisms. Distant atmospheres may remain hidden by clouds. Radio surveys may continue finding only stars and human interference. That outcome would not demonstrate that Earth is alone. It would narrow the possibilities. Scientists would learn which Martian environments remain sterile. They would place limits on biology within nearby oceans. They would rule out certain atmospheric signatures around classes of stars. The silence would gradually acquire shape. There is a difference between searching a small room and finding nothing, and searching an entire world. Humanity has examined only small rooms. Most planets have never been observed directly. Most exoplanet atmospheres remain unknown. Most radio frequencies, directions, and periods of time have received little attention. No probe has entered the oceans of Europa or Enceladus. No laboratory has examined carefully selected Martian sediment returned directly from an ancient lake. The absence of proof currently describes the beginning of the search, not its completion. This is why the evidence must be held in balance. The number of planets does not prove life. Water does not prove life. Organic molecules do not prove life. A habitable environment does not prove life. An unexplained signal does not prove intelligence. But these observations are not meaningless. They show that Earth's ingredients and broad environmental features are not confined to Earth. The universe repeatedly forms planets. It repeatedly forms carbon chemistry. It repeatedly gathers water. It creates rocky surfaces, atmospheres, energy gradients, and long-lived oceans. Nature has reconstructed many parts of the setting in which terrestrial life began. The missing observation is whether the process continues from setting to organism elsewhere. This is the honest center of the question. There is not yet proof that humanity is accompanied. There is also no scientific basis for treating Earth as the only possible living world. Evidence has moved the idea of extraterrestrial life from pure speculation into an active experimental field. Specific worlds can now be tested. Specific molecules can be measured. Specific signals can be followed. The question has entered the instruments. Perhaps the deepest clue is Earth itself. Life appeared on one small planet, built from ordinary cosmic material. The carbon inside cells was forged by earlier stars. The oxygen in water came from stellar interiors. Iron, phosphorus, nitrogen, and sulfur passed through cosmic history before gathering into the young solar system. Nothing in Earth's basic material was unique. The atoms were widespread. The laws of chemistry were universal. Gravity formed the planet through the same processes that build worlds around other stars. Somewhere within Earth's early oceans, ordinary matter crossed an extraordinary boundary. It began maintaining itself. It copied information. It changed. Over immense time, it produced forests, coral reefs, migrating animals, memory, language, and instruments capable of examining the stars. The existence of life on Earth proves that the universe contains the potential to become aware of itself. The unanswered question is whether that transformation happened only here. Perhaps distant worlds contain simple cells beneath their soil. Perhaps dark oceans move around unfamiliar ecosystems. Perhaps no other organism has reached intelligence. Perhaps ancient signals are already crossing the Milky Way. Each possibility remains open. The final proof may arrive tomorrow, or it may wait beyond many generations of searching. Science cannot choose the answer in advance. It can only build instruments sensitive enough to receive it, and standards strong enough to recognize it. For now, the evidence offers no final declaration. It offers a direction. Look toward the ancient sediments. Listen to the quiet frequencies. Pass through the frozen plumes. Separate a planet's light from the brilliance of its star. Study every unusual pattern, and release it when a simpler explanation appears. The search requires imagination to notice possibilities. It requires patience to distinguish them from proof. One day, these two qualities may meet in the same observation. A signal will repeat. A sample will contain organization that geology cannot create. An atmosphere will remain alive within every model used to explain it. The evidence will pass from one laboratory to another. It will survive new instruments and skeptical questions. Then the oldest uncertainty may gently change its form. Humanity will no longer ask whether life exists beyond Earth. It will begin asking what that life is like. But for now, there is no need to travel any farther. Let the distant planets grow soft in the mind. Let the hidden oceans settle beneath their quiet coverings of ice. Let the stars continue their slow movement through the dark. The answer does not need to arrive tonight. The universe has carried this question for billions of years. It can hold it gently while breathing becomes slower and the day begins to fade. Perhaps life is rare. Perhaps it is waiting beneath nearby ice. Perhaps distant forests turn beneath stars whose light has not yet reached Earth. Perhaps another intelligence is looking outward at this same quiet moment, wondering whether its world is alone. For tonight, every possibility may remain among the stars. There is nothing more that needs to be solved. There is nowhere else that needs to be reached. The journey has crossed ancient rivers on Mars, hidden oceans near Jupiter and Saturn, and atmospheres circling suns beyond imagination. It has listened for narrow radio signals and followed faint molecules through distant light. Now the journey can become still. Let the planets continue along their patient orbits. Let the galaxies drift beyond the edge of thought. And if sleep has not yet arrived, another quiet journey is waiting on screen. If these calm nights bring a little peace, you are always welcome to return and wander gently through the universe again, one drifting mind at a time. Sleep well, and good night.